Okay, now let's see the difference between finite element, IGA, and IBRA. So first, I'm talking about geometry. I will give you an example in finite element. So in finite element, we have, for example, this one, quadrilateral. So just a quick question. What else do we have in finite element? If I'm talking about this geometry, for example, we have quadrilateral, what else? What do you think? Triangular, so can be cubic, can be tetrahedral, and so on. Right? That's finite element. Things. I don't know. This one. And I would say in the finite element, we have, of course, nodes. And I can say this is element, right? I think that should be clear enough. Now, the same thing about IGA. What is the quote-unquote geometry in IGA? What do you think? Exactly, the paths. So I don't know, maybe we have something like this. Perhaps. So, but you know what I mean. And instead of nodes, we have control points, right? Okay, that's the first stuff. So you see nodes versus control points. And now in IGA, what is the element?
Something like a box.
Yes. Okay. So if you go to the parameter space, depending on your, I don't know, your knot factor, if you remember. Oops. Shit. I can say this is parameter space. This is the physical space. And this is the what I can say the element in IGA. Yeah, in IGA. Right. So next questions, next step. What about IBRA? Yes, we are here. We are. I mean, we will talk about IBRA, but first, yeah, I will start finite element, IG, and IBRA. Okay. So how about IBRA? Exactly. So in IBRA, basically this is the same. I can say sorry. This is. I can say this is the nerve path for the IGA, and for IBRA we have the same thing. The same thing, but I would say in the parameter space, we need to consider this boundary loop, right? The trimming curve. And you can also consider, for example, if we have trimming here, you will also have the trimming here, right? That's IBRA. Then the second thing about integration points. Let's talking about I would say these quadrilateral element. I think this is simple, right? We have I don't know, maybe this simple Gaussian integration, I would say Gaussian quadrature, and we have something like this. And if you are talking about IGA, what do you think? I give you a hint. I draw the I would say the parameter space. Well, the thing is that in IGA, this would be your those points. So you have some per element. If you are using the standard rule, but if you're using the special rule like what Manuel did, we will have different configurations of those points. But typically, I would say if you're using the standard quadrature rule for IGA, this is what will you have the integration points. Then, if we are talking about algebra with trimming situations, we need to consider two different types of knot span. So this is the, I would say, untrimmed knot span versus trimmed. The untrimmed one, I would say, it's pretty much similar with with IGA, where we have the full integration points, for example, that one. But for the trimmed one, it would be a bit different. You saw from the manual's presentations how to deal with trimming. But anyway, this is just I would say illustrations about what is the difference between finite element, IJ, and IBRAD that will lead to something that I will present to you soon. Right now, um, let's go back to these presentations. So let's keep that notes later. I will go back to that one. Well, again, this is the collaboration of the work from Satya and us from Braunschweig. Sorry before the mention those names in the presentation. But first thing first, let's talk about the workflow with integrated CAD. Oops. Well, as you can see, we have two different workflows. So the first one is the workflow from standard finite element CAE. The second one, sorry about the title, and the second one is IGA. Should be so the first one, simple. We have CAD, for example, you generate the CAD model, I don't know, from AutoCAD or whatever, and you created geometry, you created the mesh. For example, like what you did in GID yesterday, you have the CAD model, you created the mesh, finite element mesh. So we have the mesh file, sorry, the one with NDTA, and materials, and then also the parameters whatsoever. And at the end of the day, you are doing the analysis, yes, I would from that one, and you will obtain the solutions. then you go back again. This is the standard finite element, what you did yesterday. And what do you have with IGA? Simple. This one, we are not doing, I mean, from the CAD, we are not doing meshing. We just using that, I would say, the clean cut directly. We generated the geometry directly from the cut. We obtained the information, NURBS, BREF, and whatsoever. And again, on top of that, we need the information on the physics on materials. And then we do the analysis, which I will explain to you later. We have some CAD cut utilities. And at the end of the day, we have the solutions directly on the cut geometry, which we can visualize on that. So I think you should remember this from yesterday. This is basically the, I would say, the procedure on in Kratos. So first, this is for the, I would say, this is similar standard in standard final element of idea. We do the same thing. So we initialize, we do the initializations, we import the model part, and then Kratos will know about our input elements, nodes whatsoever, then doing the solving and I would say output. That's what did you learn yesterday. And I would like to emphasize that for isogeometric analysis in Kratos, yeah, this is not that simple. I mean, sorry, this is different than standard FEM. Here's basically the procedure. So we need to import the CAD and geometry models using the modelers class, the one that Ruben mentioned yesterday. And then we do kind of prepare that, I would say that models to be able to be read by Kratos. I will show it to you in a second. And then the thing is that this is, I would say, how Kratos read the geometrical input and to prepare, because you will see in a second that our input from the geometry is different than standard finite element, the, I would say, the MDPA file that you learned yesterday, because, well, you see that we don't have, no, I mean, we have different elements, I mean, definitions of elements, we have control points instead of nodes, or even if we go to IBA, we have boundary loop representations, which is quite different than standard finite element. I will show it to you in a second. But before that, just a quick reminder. We were talking about Kratos, those are the important objects, but of course, I will not talk about all of that. This is just to show to you that this is, I think, just a repetition from yesterday. All right. So the next part, I would like to talk about what do we have in IDA applications with Kratos. So if you go to Kratos, you can also open it if you have it, so we can do it together. So as you can see that from yesterday, Kratos can be divided into two different parts, the core and the applications. So since we are here as I would say researchers who will do IGA, we have here IGA applications. By the way, I just have a quick remark about IGA applications that we have the existing one here. This is, I would say, how to say that this is derived from the actual structural mechanics application. So what we have here is quite similar to what we have in structural mechanics applications, and this IDA applications will be applied for at this moment, I would say, for structural mechanics applications, for example, for structures. Here we don't have fluid elements, we don't have convection diffusion elements. We will talk about that later. So in Kratos, I would say this is typical that we have. If you remember, if I go back to these slides, okay, so you see the Kratos objects, we have elements, conditions, blah, blah, blah. And this is what we have also in the IG applications. We have conditions, we have elements, we have modelers, we have process, we have solvers, we have utilities, and so on. I will show it to you one by one. So first, I think this is the easier one, the element. So custom elements is the, I would say, is the collections of the elements. At this point, we only have the structural elements. For example, you can see we have the couple of isogeometric shell element, membrane element, class element, and so on. This is, I would say, the custom elements. So this is self-explanatory. So if you want, I can show it to you one element. For example, this is shell element. So this is we have, for example, functions to calculate the left-hand side matrix and right-hand side matrix. This is following what we have already presented on first day. We have kinematics, we have the geometrical descriptions, we have also to formulate the and we see the stimulus method and so on. This is
large information elements or small?
this is what the information is. Exactly. I just want to show that that's the typically that we do to create the elements. We have these functions to compute the this is we compute the elements difference matrix here. This yeah. So left hand side matrix, right hand side matrix, for example. This is just a glimpse to show it to you. So one of the most important functions that we have in the elements. Yeah, I think that's clear about the custom elements. And then what do we have in the custom conditions? So as Ruben mentioned yesterday, in the conditions, we apply the conditions or I would say it can be a Neumann boundary condition or Dirichlet boundary conditions. In this case, if you remember my presentations from the third sessions, I have already implemented weak boundary conditions, penalty, Lagrange multiplier niches. So this is where you implement that. So we have these examples of coupling Lagrange conditions, coupling boundary conditions. This is for also for the boundary conditions and so on. This is in the custom conditions. Then now we have the custom modelers. This is the most, I would say, important thing for IGA. This is, I would say, an object to interact, to create and update the CAD models. To be honest, we do it in a separate way. So we have the modelers in the core and modelers in the ID applications. So what do we have in the core? I will go to the core maybe in a couple of minutes. So in the core, we will import the CAD geometries for our input, and we do the well. I will explain to you what do we mean by meshing of or tessellation of the CAD geometries. But this is the most important thing to import the CAD geometries. That's I would say what do we have in the core for the modelers. And in the IJ applications, why do we have modular separately? Again, like I told you, this is I would say the for the structural problems. So we create we assign, for example, okay, this is this element is Kirchhoff law, this is boundary consent, so on. We assign it here in this custom modulars in the IJ applications. So, for example, here we have this one, IGA modular, for example. This is yeah, for here to create the element. I would say, sorry, to assign a certain, I would say, cat to create an element. I would say, I mean, this is here, for example, the type of element and so on. To create the elements on top of your cats. Then we have custom processes. Well, this is, I can say in one sentence, this is the algorithms to solve for different problems at a certain steps. So if you remember, we have two different loops in Kratos, loop, time loop and nonlinear loop. And then we have execute before solutions, blah, 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 a lot of steps that Ruben showed yesterday. And for example, in my case is to get, I would say, the Nietzsche stabilization factor. I do it here for analysis. And we have also a custom solver. This is if you need a specific solver which is not available in the core for a specific computations, we put it in custom solvers. And for the strategies, this is the general steps in finite elements algorithm, for example, to let's say prediction, solving, convergence, control, and the utilities means, well, yeah, I think well, some extra stuff that you want to put in the utilities here, and it is not bounded from the steps. Like um, we can call this custom anything that you implement in custom utilities anytime in the computational steps. And we have also a bunch of Python interface to do a lot of things, for example, to the mainstream of the ID applications, for the output, for the process, and so on. Here, if we don't have to many Python scripts compared to the other applications, but for example, this is one of the Python script for the output. So we do it in Python interface because this is easier. Imagine you do the output stuff in C++, and how complicated it is. So for that one, we use Python. So, so last but not least, we have the test. This is important. I mean, to do the good way of coding, we have would say CPP test, for example. We have also some small examples. This is for path coupling. We have also kind of this one. We have also the test.
So when you develop a new implementation, you have to pass all these tests.
Exactly.
All of them.
All of them. So whenever you do some changes in this, I would say in IE application, you put your new element. I don't sorry, not a new. Let's say new field is to compute one second. You need to do. You need to create the unit test, and you need to make sure that the all tests are passed.
Let's say you have to create a test for your implementation,
Exactly.
and all of the other tests have to be passed.
Exactly. Exactly. So this is, I would say, one important for a good practice of code. Then I'll show you here. We have this CPP file called IG application variable. This is, I would say, if you have special variables for your applications, which is, for example, here, for example, this variables need to stabilization factor. This is the variable that I need for path coupling. And this variable is not needed for the other applications. I mean, for the applications, they don't need this variables. In that case, you store or you assign the variables here in the IB applications variable. And this one, if I search it, I mean,
sorry, what are the variables again?
Variables is that I would say the variables that you only use in a certain application.
Okay, but where are them?
In the ID applications variables. So here, sorry. Here. So you got the ID applications and then
Yeah.
So are these variables only correlated to patching, to coupling?
to copy. Yes, for example. I mean, of course, you can go to my custom conditions, to my nature coupling conditions, and put that I assign that variables. But I mean, I put it here, so I can call this in, for example, in custom process in the Python test. So I mean, if I insert ID applications, I can call this. So yeah, if I type niches values in fact, okay, I know that this is double variable that I put it for the. And yeah, last but not least, in Kratos, we need to, I would say, uh, yeah, we need to register the elements, conditions, variables in this IGA application.cp. This is, I would say, otherwise, well, yeah, you cannot call the elements or the conditions of the variables. So, for example, here we register class element, we register the shell 3p element, and so on. So far, so good. I think that's what we have inside the IGA applications. Do you have some questions before we go to the next step? Well, I think this is just very quick explanations about what we have. I think the next step will be more interesting about this what we call IUI exchange format or our input files. So if you remember from yesterday, we have three inputs, right? The MDPA one for the, I would say, for the final element mass, the materials, and the project parameters. Here for I would say for ID applications in Kratos, we have more. We have geometry.cat.json. We store it in JSON file instead of MDPA. Materials is the same. Project parameters is the same, and we have physics.iga. This is, I would say, I will show it to you later what this physics.iga means, because this is a bit different than standard format. And this is self-explanatory from the I would say from the title requirements IGA. So this is the script for doing, I would say, refinement. Okay. Right. Before we continue,
Sorry, Ricky, and
yes.
all these files have been taken from Rhino.
Exactly. We will do it in the afternoon session. So we have Rhino, we have our plugin to generate the input, but we will not do it. We will do it later. So here, if I suggest that I already uploaded one example. Yeah, sorry, here. I think I put it in our Google Drive. So let's sorry, not that one. So you go to Google Drive. You can try to download this, and we will. I would say this is one example of the input. We will go and see that input again.
In day breakdown. Yeah.
Day 4, I think. Yeah, because we supposed to be
Yeah,
for
day-
yes,
they oh, but yeah.
yeah.
It's called day. Yeah, in the name of
But that's not right. Sorry, I missed the point.
No, I mean, what I want to say is that try to download it now. We would, I mean, this is the input file, one of the example of input file. We will, I will like to show it to you.
But that will use Okay.
No, this is the
Just whites,
Yeah.
just.
Yes, well, I mean, here the intention is to show you, well, the example of the inputs. So just, I mean, you can put it anywhere.
Just open them.
Yeah, so it shouldn't be like with these other files too.
No, no.
No, I mean, well, I'm using Visual Studio Code to open that one. You can use, I mean, text editor or whatever. It's up to you. Just tell me,
Once even I didn't get in a verification code, otherwise I can't try.
yeah, we can.
What? I hope it doesn't take more than one.
Oh, wait.
Okay. Presentation. Or just for not did. But you said okay, three. No. Yeah, I'm sorry. Yeah. Down, down,
All right.
down, down.
Okay, first, let's talk about this geometry. By the way, this is the, I would say, the structural models of this example. So we have, I would say, single paths. So I put the Dirichlet boundary conditions on the left hand side and Neumann boundary conditions on the right hand side. Oops. Okay. So why do we call this IBRA exchange format? Because we directly generated, this is generated from Rhino, but we generated the IBRA, I would say the IBRA format instead of the IJ format. Oops. Okay. So in the IBRA format, if you remember that we have the, I would say, also deal with this one. I think this is the most important thing, the topological things. So any kind of surface can be constructed from I don't know, edges and vertices. So forget about this one. Consider these things. So these things, these paths can be, I would say, constructed by these eights, these eights, these eights, and you see E1, E2, E3 till E6, and then V1 till V6. They constructed this geometry. That's why here, if you go to your geometry.cat.json, you can see that we have well, if we have faces, edges, vertices. Okay, let's go to the faces. So you go to the faces. This is, I would say,
Sorry, Vicky, which folder is that?
No, this is the
It's not
the one you download. This is the one you download from. Yeah, you have to download it from. This is the one from the GECKO drive.
Yeah.
Yeah.
well, I mean, I just open it here using the Visual Studio Code to make it easy. You can open it with editors, text editor, or whatever. I just want to show it to you about
Yeah,
the
it's
input.
big one. The one you downloaded is for the.
Um,
So it looks very modern, no? No, it's like my agenda. Okay. It looks.
Right. So, well, I put the model here. In this model, we have only single paths. So that's why if you go to these faces, we only have one face here, which is we assign it with this UFI2. This means we are talking about this surface. And if you see these input files, we have the information of that surface. The the degrees of, I mean, the polynomial degree, the Knot factors, and the control points. I think this is self-explanatory for you.
In the control points, you have the coordinates and the weights.
We have the coordinates and weights, exactly x, y, z, w. And what does make it spatial is that we have if you I mean I'm talking about the face, we have these boundary loops because we are talking about Ibra. If you see that one path, if I go to the parameter space, it has, I would say, it's constructed by four trimming curves or four edges. So 1, 2, 3, 4. That's why if you go to the boundary loop, you can see that. By the way, we have two types of loop, outer loop and inner loop. In this case, we only have the outer loop because if you have something like this, we will have also something like this. So we will have five, I would say five linear loops. But in this case, in the example that I uploaded, we only have four trimming curves.
So Ricky, in this case, for the trimming curves, the control points you have are control points in the parameter space.
Exactly. Yeah, on the points of those trimming curves. So here, for example, this is trimming curve with index 0. I don't know, maybe this guy. And we generate information, the polynomial review of that, the trimming curve, not factor, control points. So basically that's the structure. In this case, we have 1, 2, 3, and 4. And if you see in the inputs about embedded loops, embedded edges, embedded points, this is the advanced format of these things, which I will not cover today. Just very advanced things. So I will skip that. And now we have the edges. So here the trimming curves are lying in the parameter space, and the edges basically is that guy in the physical space. That's it. That's basically the edges. So as you can see here in the edges. So for example, edges with edge with brep ID 3. It has the topology, it refers to brep ID 2, so it means that it refers to this guy, to the surface 2, and trim index 0. So this guy. So H3 means the trimming curve 0 in the physical space. And the same thing, for example, brep ID 4. brep ID 4, I'm sorry, H with brep ID 4 means that, okay, this guy, surface 2, I don't know, trim curve 1, so yeah, that guy, and so on, and so on.
Sorry, can you explain again? I think.
No. So the topology, the first line, brep ID 2, it will refer to which faces, which surface. Right, so if you remember, we have a surface with brep ID 2. So it means that H3 lies on this face. Imagine if you have multiple patches, so it can be the other
You need
guy.
to identify to which patch it is.
Exactly. And then trim index means that this guy. So it's always the same case. We have, for example, 4 trimming curves, then we will have 4 edges, at least in this case. Why this is important, I will show it to you in a second. So yes, we have H with brep ID 3, brep ID 4, brep ID 5, brep ID 6. So in this input, you can clearly see that we don't have we have a completely different structure than the NDPA from yesterday. From the NDPA yesterday, straightforward. Element 1, connectivity, I would say to the nodes 1, nodes 2, nodes 3 for triangle, for example, but this one is completely different. We just have the informations of patches, edges, vertices. And from this information, from the input, Kratos, it will be read from Kratos. And how Kratos be able to read all of this data, I will show it to you. I don't know, together with me for 1 second. All right, that's about the geometry data. So let's go step by steps. Okay, I think I will do this one. Okay, let's go to physics. Physics.iga.json. So physics means that we assign the element conditions and coupling conditions to either to the patches or to the edges. So in this case, like I said, we are working on the structural mechanics problem. So I would like to assign this one um, as a shell element. How do I do that? How do I do these things? So here, BREP ID2. So BREP ID2 is this guy. This guy, I assign it as shell element. Check. Then now I would like to assign this line or this edge as I would say I would like to assign the nearby boundary conditions, these support boundary conditions. But to assign this line or this edge as as a nearby boundary conditions, I need the information of the IDs. So you remember if you go back to geometry.cat.json.
Sorry, Ricky, I have a question.
Yes.
In the left side, supposing you choose an open vector, you could apply strongly the usual boundary condition in the first one and in the last one.
Yes.
So in those you apply them strongly and in
Wait, we will talk about that later, but in this example, I impose it weekly.
all of the conditions.
So I impose this
You
weekly.
put it well on the corners, but.
We will talk about that later.
Okay.
Because if just 2 point, you have like 1,000, you do 2 and then. So if you work with it.
But in this particular example, I will assign support penalty condition. I assign weekly, well, just for the demonstrations. So I assign that support penalty conditions on edge BREP. So edge 3, for example. And here I assign this guy edge number 5. I assign the Neumann boundary conditions. This load conditions. So that's basically, I would say, the structure. So we have the geometry with, faces, edges, and we assign these faces and edges as element or conditions or maybe later if we have time coupling conditions.
Hey, Ricky?
Yeah.
Why do we need to specify also the shape function negative order?
Okay, good questions. Okay, I think Nicolo knows the answer.
Yeah.
You know, but no.
No.
I would like to actually no. Just thinking, why do we need this? Because I know that the advantage of nerves basis functions or spline defense that we have higher continuity. So I can assign this as p equals to 4. I mean, let's say I'm doing p refinement, p equals to 9, p equals to 10, whatever. But for the shell element, we only need the second derivative for moment and third derivative for shell, for example. So it's just to limit I would say this is for the optimizations. Otherwise, we need to compute. I mean, the thing is that we store the shape functions at the beginning before we enter the loop. So we compute the shape function first, we store it in an iterator, then we will call that in the instead of computation. So imagine that if you have p equals to 10, we need to compute shape functions, the derivative of shape functions up until the 10th derivative, and that would be very, do you want to add something?
Yeah, with this condition, we are actually then on Kratos, we will create a Gauss point for integrating the boundary and the element. No, I mean with this,
Yes,
this we were saying on that line on
We will
on the left.
We will talk about integrations points later.
Yeah, but here what we are saying then create on this line.
Yes, exactly.
And compute
It means that
function up to that
derivative. So for
It's
instance,
Gauss point. Yeah,
those ones, because we only need the derivative up until that level.
But it has to do with the shell elements you're you're using. Let's
Yeah.
say.
Okay. For example, if you have class element, simple class with only first letter, for example, you put one. Depends on case by case. Alright. And for the materials.json, I think the first part, well, 100% similar like what we have yesterday. This is the, I would say, the materials linear elastic stress, for example, and we assign the value thickness, Young's modulus, Poisson ratio, density, blah blah blah. You can also change it to another constitutive law. It depends on composite, whatever. And the thing is that since yeah, for this particular example, I assign weak boundary conditions here using a penalty method. I need the information of the penalty factor. I put it here. The materials. And then for the project parameters, well, almost all of these lists are identical with what we already told yesterday, except one thing. This one, model. So you go to project parameters, you go to the model. So this one, we will go to the get.io modeler functions in Kratos, and this will read our geometry.get.json. So it will process the data, I mean, the information of here. You remember the face edges, vertices, and yeah, basically the input, just input out with the input files. Sorry, let's go to the third one. The third one, it's related to the physics file. So yeah, so to wait which one is the element, which one is the conditions, and so on. This is in what we call IDA model. And the second one, we have also refinement modeler. So this is something we can do the refinement here. So we can put, I would say, well, now you can argue why don't we do the refinement in Rhino, for example? Why do we need this one? Because there are two reasons basically. If you do the refinement in Rhino, you will have, I would say, well, the size of the file will be higher if you do the refinement in Rhino. And you can imagine you do the refinement in Rhino and you have this input with well, I don't know, 1 MB. I mean, so I would say extremely. So we can mitigate that by doing it here. And the second reason is that doing refinement in Rhino is not that, I would say, in Rhino you can only do the refinement, for example, not insertions. So this is by the factor of 2. So for example, if I want to have 10 elements, it's, yeah, Rhino cannot do that. Then we can do that, but we need to create another plugin of counts. Not that easy. So to avoid that, we created it here. We have a functions to do P refinement, H refinement, and K refinement in Kratos. Okay. So what do you have questions, doubts about our input files? All right, let's do the following. I just want to test. So can you try to run these input files? I mean, we have everything. You just need to go to the command and then try to run Kratos. Just to test it. If you are able to run this script, you should be able to see this output. Try this. Yeah, I mean this.
Sweet. Yeah, we got anything but one.
Okay.
Five files.
Yes. Don't know the five. All right. So I think
What did you say?
No body name.
Yes, export. Because you have to export
yeah,
Final.
export.
Kratos.
Okay, we
Yeah, Kratos and
Yeah.
to
to if the environment.
the parser to.
I can help
Where
you
Kratos
with during the during coffee break.
I will send you.
Maybe this is why I ask you to do this file. In this program, set Kratos.
No.
Well, you can do that. It's
Yeah, yeah.
theoretically. I mean, if you don't have the path, you put it inside the let's say the executable file.
Yeah, but every time you have to do it, but and you.
Yeah, we will
gonna
send
send
you
you.
during the coffee
I'm
break.
gonna send you a line. You have to-
So anyway, if you open this one, let's open the shell to Postgres and shell to integration domain, just to just those two things. Those two, and I just want to show you the output files. The shell underscore 2.post.res, shell underscore 2 underscore integration domain. Just open those two files. Then basically this is the output. For example, this is the displacement of the, we have 15 control points in this particular example. This is the Cauchy stress, by the way, you can see the stress is calculated on Gauss points. So this is the, I would say Gauss points 1 till Gauss point 32. I can
So that you don't have to reevaluate again the basis functions.
yes, I mean, inside the IB applications, I would say this is the final. I mean, we have the functions left in finalized output functions to compute the consistence. So this is already, I would say this is already consistence. And so on and so forth. And the other file, this is just the collections of the integration points. So the coordinate of the integration points in the parameter space. In this case, we have 32 Gauss points.
You can go back the other file.
Yes.
And the displacements are computed on the nodes then?
Yes, exactly. Control points.
Okay.
So
So
later,
in integration points, you have four numbers, two the coordinates and the other two.
this is X, Y, Z.
No, in the integration domain fact.
Okay. This is ID. The I would say ID of those points. This refers to
The BBF ID.
ID2, X2, and
Then the-
coordinate in parameter space CE.
Okay.
Can I ask you, would it mean that the displacements are computed on the control points? I mean, if the control points could
No,
be,
the Gauss points.
no, the
No, the
displacements,
Yes,
yeah, the control points could be also outside the true geometry.
exactly. So be careful.
So no physical meaning.
No physical meaning. It's just, I would say, you solve K times Q equals to F, you solve that U. This is the, I mean, if, yeah, you're correct. If you want to, for example, compute, I don't know, displacement at this particular point, we have a functions, Python functions, Python interface to compute. So you remember this. So you put the coordinate of that point and we compute the displacement at that position. So do another one more step post processing. But as you see that this is not quite, I would say, yeah, we need to do one more step, or you can use our plugin. We will install this after lunch. You can use our plugin. I mean, in the plugin, it will automatically calculate it. All of those.
So they go and say,
So you can,
If you use paradigm for visualizing the results,
Now,
at this point, not yet. So the thing is that what you can do, we have the output result or something like that, and we need to create the 50K output for IPA. But at this moment, we don't have it yet, but it's possible. For example, we call it
yeah, we will see the.
you have the results, the output, then you port it to one. It's possible. I mean, at least in my
No,
case,
not the problem, but in
Yeah.
for the future, we are there.
well,
For K, but for the moment we have like a non-made post process on Python that we see same.
exactly. In my case, well, I'm using the plugin. We need to output the result. But yeah, again, this is for the case of structural mechanics. So in your case, particular case, you need to do the. I mean, I don't think that you need this plugin to visualize the result. I mean, what I want to say is that you can use this plugin to generate the, but for the output, you can do anything that you want. That's my take-home message for you guys. Right. Now, I have, I would say, I would like to note that these things, the question that you asked, what if we have strong conditions instead of the weak one? Because in that particular example, we have, I would say, it's an example for weak one. Yes, we can do that. I mean, we can impose these strong boundary conditions. And how to assign that? I mean, in the physics file, we tell that okay, this line is fixed. This line is fixed, or that point is fixed, or that point, that line. I mean, all of the points on that line are fixed. All of the points on that line is fixed, and so on. So what I want to say is that in the physics we can manage to do that. This is for, I would say, the strongly looked boundary conditions, and also for coupling. We have, I would say, this is all of the combinations of I would say of the coupling that are doable in the physics. So we can couple surface with surface. We can couple surface with curve. We can couple surface with surface at a certain point. We can also couple, I would say, surface with curve at a point, curve with curve, and curve with curve at a point.
when you mean curve would be, for example, a truss element.
Yes, exactly. Truss with, I don't know, beam, for example. So it's doable to do that with our eyedrops in our eyes of the same small. And this is the example, like what we have in our particular, I would say, this our particular case. This is we apply the weak boundary conditions on that line or at a point, or line. And in, for example, in 3D, in manual cases, of course, we can extend this concept. So we have the volume, we assign, I would say, a surface boundary conditions or a line boundary condition or point boundary conditions. Yeah, I think this is, yeah, I would say, project parameters. I don't want to repeat what Ruben already said yesterday. This is the same thing, I would say. So we have I would say, analysis type, linear or non-linear. This is just the criteria for the convergence. The type of linear solver, we have a lot in Kratos, sparse, LU, Paradiso, so on. And yeah, this is the modeler. I already talked about that, to basically to get the input and to assign element conditions. This is process list. You remember yesterday to assign the spatial things. This one we assign these the flat and monument boundary conditions in the process. I mean, you can found it in project parameters. So in this case, I assign that block here. Simple example. And of course, Ruben told you from you yesterday, we can generate a Python script to modify this value. We can do the same with this IPA. And also the support if you want to put also initial support. And this is for the output. So for example, here, I would like to, I would say, visualize the displacement at the, as a nodal, I would say at the control points. This is, I would say, I would like to compute the stresses on the integration points. This is the additional process to show the integration points.
Vicky, where do you see that?
Project parameters.json.
Yeah, but where do you define that you want to calculate the stresses in the Gauss points? Is there a specific line?
$127.
Okay. But you could say as well, instead of integration point results, control point results, this.
Well,
No, because we don't know the basis function at the control point. We just know the basis function at the Gauss point.
Okay.
So at the beginning, we compute all the basis function at the Gauss point. And we use then the summation.
it's basically this.
Because it will be too expensive to compute also. And also they can be outside. So you don't know the basis function outside the. Yeah,
So and with Python, I already talked about that. And last but not least, obviously, the Python script to one. So this one, okay, look, we also need to import some, I would say, these structural mechanics applications because we use some of process some utilities from structural mechanics applications. So for example, if I want to use some utilities functions from linear solver applications, I need to also import that one.
And in this specific file, where are we creating the analysis stage?
In structural mechanics analysis. In the structural mechanics analysis, structural mechanics applications, we have the script.
So when you are calling structural mechanic analysis with model,
this one,
you are creating the analysis stage.
Exactly. Yes.
Because structural mechanics
I can show it to you.
derived from the analysis stage. It's correct.
Yes. So I can show it to you. So this is, for example, the typical, I would say, main Kratos Python file for the ID application. So if I go for the structural mechanics, see, this is the analysis stage. One, I would say, it's parent class. Yes.
From analysis stage.
Exactly. I mean, this is, I would like to say, this is for the case of structural mechanics. For example, if you want to derive it from convex individual, for example, yes, you can do the same. then with that, I think we can just stop here.
And can you mention a bit for the next session that the element and the condition? Because otherwise they will not understand.
Yes. Okay, for the next sessions, this is the important things that I would like to show you. This stuff. This quadrature point based simulations, because for IDA, that's why at the very first place I explained to you this concept. I will refer. I mean, I will start with this one. I would like to emphasize the importance of integration points in IDA, because just a teaser, we use integration point as our elements. So we don't have elements in IDA. Indeed, we can say this is the element, the one the non-zero not spans, but in IDA I would say IDA in Kratos, we use integration points as an element.
Let's say a set of integration points is an element.
No, so this is, if you see, we have 4 times 4 16 Gauss points, so we have 16 elements because we, I mean, so this is this one, this point, this one element. It's a bit complicated. This is just a teaser. I will explain it to you after the video.
In Kratos, and in Kratos, one Gauss point is
One Gauss point is one element.
That's for being able to use all the methods from the structural mechanics, let's say.
they did like that. I actually, I mean, they couldn't use like a different name, but they choose to use that name. So for the moment, we are stick with that name.
So, well, I don't want to mix that concept to you guys. That's why I have
Yeah.
not thought about that. But yeah, that's the teaser for the next one. This
And same for like conditions.
exactly
So
this
one
one.
condition is one of those points on the boundary, on one integration point for integrating boundary. Okay, so exactly the same for the other.
Well, just a teaser. I will explain it again. So this is what we have in standard finite elements. So you have the geometry, you have square, sorry, quadratic quad, for example, or triangle. And then that triangle is the element. So you have the geometry and you have the element, which is basically the geometry. Triangle element, quadrilateral, right? In IDA, we have the geometry, which is this guy, the surface, or the edge or the curve. And then we have the quadrature point. We have the Gauss points. And that Gauss point is the element. Well, I will try to explain it to you later. But okay. I will explain the first one.
No,
For the first one, it's clear, right?
Yes.
Okay, that's enough. That's enough. Right. So I would like to remind or make a review about this concept of hybrid and IGA. So the most important thing is that in finite element we have, I would say, the defined geometry or the fixed geometry. I would say this quadrilateral, this triangular, these solids. It can be applied for any kind of, let's say, application, right? But here in IGA, it really depends on your, I would say, on your paths. It can be anything. Even more if you have something like training. Right. That's why here I would like to show you about the the second topic will be the Kratos objects related to IGA, and I would say the most important objects that we need to know in IGA are those with the geometries and the quadrature points. How we deal with those two things in Kratos. Right. So let's open slides. All right, so basically just a quick review again. The Kratos objects, we have all of those parts, but I will skip some, well, most of them. And well, let's revisit this model once more because I skipped that part. Right, so the definition of modeler, this is, I would say, modeler is designed again to interact, create, and update the model from the analysis. So in that case, I will show it to you in the board. So let's wait the code. Kratos. So now I will show something which is I would say implemented in the core, not in our IDE application, because this can be used for I mean anyone can use it. So you can go to Kratos and modular, and then get IO modular. So in this, I would say in this get IO modular, yeah, I would say this is where you, I would say, read the Kratos. So
Sorry, where is it?
again, underscore IO underscore modular. I would say that this is I would say the functions to set up the geometrical model. As you can see here, we create the model part, CAD model part, and I would say we get the model part from this geometry.get.json. So all of the information from the one we put out there, they are intercepted before to the blade, will be read in these functions. And at the end here, we will have, I would say this CAD model part. So I would say we construct the model part, but I just want to let you know that this is basically the workflow in Kratos, and also we have the similar things for the output. So I mean to I would say to generate the output files that we have showed before. So that's it. That's the modular. Go back to the presentations. And on top of the modular, we have this particular classes IO. So IO provides different information of input of procedure. So the modular will call this IO, Kratos IO, to read and write different formats. So again, if you go to the code, Kratos core, input output, and you can see a lot of stuff here. So in our case, we will use this get underscore.json for input, but you can see that, for example, this is the input Kratos input out for example, for ASCII, for VTK, but here we have I would say get.json.input. This is for IDA. Well, I don't know, maybe sooner or later, if you're working in Kratos, I just want to show you that this is a high level because it's the core. You need to know about the template in C++. Anyway, just a quick piece. But so you can see that we have functions to read all of the CAD geometries here and provide the model part. So basically, this is just an example. If you I want these things. So you can see the model part here. This is the I would say the model part of our input here. In this example, if you remember this example, we have 15 control points. That's why here we have 15 nodes. And if you also remember by heart that we have 1, 2, 3, 4, 5, 6, 7, 8, we have 8, I would say, non-zero node spans, and for each node span we have 4 ghost points. That's why we have 32 ghost points. And Nicolo told you before that in IDA the integration points are the elements. That's why here we have 32 elements. I will tell it to you later about that, but just an illustration. So this cat JSON input dot that one will create this model part. I mean generated the model part from the data, and sorry, for the input from the data. And by the way, this is the support. I mean, this guy. We don't want to spend so much about this because this is not the most important thing. But the most important thing is this one, this geometry. So yeah, well, this is, I would say, the Kratos geometry for the standard finite element. So for example, you see here geometry, we have triangles and quad, I would say standard finite element, simple. And then the element is, you can say element triangle, element quadrilateral. Yeah. Well, if you are, I would say, advanced in C++, we can say this is a bridge pattern template. Anyway, this is in, I would say, standard finite element. So we have geometry, which is either triangle, quadrilateral, solids, and we have that element. We will go back with so if you go to the core again, so core Kratos geometries, you will see that here we have line geometries. We have, for example, quadrilateral to the not with 9 nodes, with 4 nodes whatsoever. This is, I would say, there are a lot of types of short and triangles. And what do we have for IGA in this geometries?
Nerve surface.
Nerve surface, exactly. Here you see we have nerves curve geometry, we have nerves curve form geometry, nerves surface, nerves volume, for example, I would say, for example, Marvel did that. Anyway, but if you go it up, you will also see these things. We have curve on surface, surface, and now the questions. What are the differences? Why do we have the surface than VLAP surface? Why? Okay, I will let you know. Second. So the thing is that this is designed, by the way, I should mention here, his name Tobias Asmacher. This is designed by him, this concept. So let's start from the left side, the NURBS geometry. The NURBS geometry, basically that guy, the surface or the curve or the volume. And all of the informations related to that, the computations of, I would say, shape functions, basis functions, the derivatives, and blah, 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 will be, I would say, will be called in this geometry. So NURBS geometry, simple, easy, IGA, I would say. The reason why we have VLAP geometry is that IBRA, because we have the IBRA stuff, which is sometimes we have these things. So we have the surface, I would say the initial surface, and we do training, for example. And we need to, I would say, store the informations in VLAP geometry. That's, I would say, you see that delimiting the geometry. So if you cut the geometries, you need also the information about that. And we also have coupling geometries. This is for my stuff to couple more than one patches. Well, for the NURBS geometry, well, as you guess, we have NURBS for the curve, for the surface, for the volume. And by the way, if you see the constructors, so we need all of the informations. We need the informations of polynomial degree. We need the information of knot factors, weights. Makes sense, right? Basically, this guy, which we can generate from the input. And the rest also the same.
Sorry, Ricky, where is the parsing of all the data from the input files?
What do you mean by parsing? To
Let's see, how do you extract the data from the input file? Where you have all that methods?
I think I don't have time. I will talk to it personally because I mean, I know it's can be some of input if you look in details. Jason that Jason can underscore Jason input you'll find parser status. But I'm sorry, we are running out of time, so I will talk to you first. Okay, then for the VLAP geometry, you see the constructor is that the NURBS itself. I mean, we need the information of the NURBS geometry, and we need the information of the trimming curve, the outer loop or the inner loop or both. In this case, we have the outer loop. I mean, we construct this as a VLAP geometry. So, last but not least, coupling the geometry. Of course, you need the master and the slave. And also, we have another constructor for more than two geometries. This is we have multiple constructors so in one class. Okay, now this idea, the quadrature point-based relations. Okay, the idea is that we have a new approach using quadrature point geometries as the elements. The questions on why. Let's go back to this picture. Okay, let's talk about the IGA. If we are in IGA, I can say, okay, we can decide the element. I know we have this NURBS geometry, right? Let's say we have the NURBS geometry, and we can decide that the elements is the non-zero nodes. That's in IGA simple. We can do that. We don't even need the points. I mean, we can say this is the element. I mean, so the element numbers depend on, I don't know, number of non-zero nodes. If we are talking about the standard IGA, easy. But why don't we do that in Kratos? Why? Because we are not dealing with simple IGA. We are dealing with Ibra. With Ibra, all right, simple for this one, for the untrimmed, untrimmed geometry. You can say this is one element, two element, three element, four element, and for each element we have 4 Gauss points. But how about this guy, the trim one? I don't know the number of Gauss points. This is a special element. And it's like, how to say that? It's uncertain, I would say. It depends on your method. Manual taught you about several methods, how to do that. But anyway, what I want to say is that, well, we can have usually more Gauss points in trim, I would say trim span. So the main reason is that to avoid these things, we just decide, okay, if you go to the, I would say deep level of these integration points, the integration point, one integration point has the information that it needs to compute derivatives, to compute the shape functions, right? Because, okay, I know these Gauss points, for example, will, I don't know, will relate to those control points. And we know the position of this, we will compute eventually at the end the shape functions or the derivative of shape functions at that point. So it knows all of the information from the geometry.
I'm not getting the basics, because let's say when you have the weak form, you have integral over the volume of the surface.
But at the end, you will have your integral, that's talking about volume, will be summations, right? You will do numerical relations.
Okay, so you are dividing your domain into different subdomains.
Exactly.
Classically, IGA is the non-zero node span.
Exactly.
But in this case, you find a point, not the surface. So that's what I don't get.
What do you mean by point? I mean, this, if you go to this integral, I don't know. This can be a summation of something like that. So we have the Gauss points, right? For example, in this case, 4 times 8, 32 Gauss points. This is the sum. You can compute the integral by doing the summations of the, I would say, from the point. Let's talking about the, I don't know how to say that, the, if you remember, we remember the tutorial that I gave it to you, that at the end of the day, we not do it analytically, we do it numerically.
No, of course, yeah. Of course. What I'm saying is that the whole domain is the, let's say, the union of all your elements. So in this case, you have points as elements.
We have points as well. It's just the name, I would say. It's just the name that
We just
it's just, I would say, so we call this guy element, which finite element, we call this guy an element, this one, what we quadrilateral, and one quadrilateral element has 4 integration points. But at the end of the day, I would like to say that you compute based on those 4 points, right? It's the same thing here. But we call this as the element, yes, because in algebra particularly, you will don't know how many integration points or quadrature points that.
So let's say you are not going to loop
over the
you're
element.
going to loop over the control point.
You will look over the
Over
over the
the
exactly. Yeah.
So
We still do that exactly.
that's still there.
Yeah, it's still there
Okay.
because we need to distinguish between the trim and untrim element.
But you loop over the integration point. So
We look over
and
yes
you,
the
and you
point.
assemble considering the integration.
Yeah.
Exactly.
And they will wait because first we divide it in a north span, then we find all the delta point. We assign them a weight, and the weight of its integration corresponds to the north spans where they are, like the portion of area they are.
Exactly. If you cut
So at
something,
the end
you have
it's-
different weight.
They used weights to find the bound.
To define the area of your cut.
Yeah, the area of influence of your.
And then you add that.
Yes, in the end you.
So that's why what Manuel did back then is that what he needs is just the points.
Yeah.
Right. So exactly the points. Then we have the, I would say, the summations or the assembly, the contributions of all those points, and we will have the say the global series. So from him, so we'll generate the list of points. Then that one will transfer to Kratos. And we will do the same thing actually in the case of Iva. The thing is that with Rhino, we just generate these input data, but at the end of the day, we will have these points. Same thing, like manual. Yeah, basically that's the idea. Why we have, we go back to this slide. Why we have this idea, novel codes using quadrature. By the way, this concept is not only applied for the ID applications. You can imagine for the material point method and BM. They also use the same thing. So they at the end of the day they just assemble the points, not the not the elements. So I would say classical triangles or so. Well, one can argue this is not novel. There is a massless element techniques, but yeah, that's inspired from that. So yeah, I think that's all for my side. Now I will pass the button to Nico. He will provide you some examples. What I called just a theoretical part of the Kratos idea in Kratos, but now we will do some stuff.
Yeah, we can do an exercise on Kratos. I did it on Mac, I tried on Windows of Andrea and on Linux, so everybody will do it with success. Then, for who is ready, and then we will come back. On another Windows of Visual Studio, I suggest you to open your Kratos. So to have two different windows of Visual Studio, one with Kratos and the other with your folder. Okay, so I have here my Kratos open, and if I switch with Windows, here I have the other. Okay, here we will have our main IGA.py where we will call Kratos and we will launch our simulation.
So we just open two windows.
Yeah, one with our folder as you did, and the other with your Kratos,
The very-
the one you have compiled.
This one, or if you change it,
Yeah, you just need to have two different windows.
one you can do is yours. If you think you wanna have one window, you just try to use that. And there's usually, yeah, exactly.
It's okay, Joan? Okay, so a trick, if you Control P, if you write Control P, you should have to able to search with Command P or like for macros and Control P for the others, and search for configure.sh. That is the one you use for compiling. Okay. Continue. We have opened two windows of Visual Studio. One with our folder that you downloaded, and the other with Kratos. Yeah. And in Kratos, with Control P, you can search in all the scripts you have in Kratos. If you text,
Which one? Because we also have a lot.
yes, the one that is in scripts. I mean, you can also find it in scripts.
But
What is this configuration?
Yeah, it's a configuration. We are depends. Let's say if we have the ideal application, everybody has the idea.
but in Windows it's not bad.
Don't remember. And
.sh is Linux.
yes, yeah, your configure file, the one you compiled yesterday.
I don't know. Yeah.
Well, in Mac, that will be with.
Yes, it will be a state.
No, you compiled this one, standard configure Mac, no? This one. So for you, it's this one.
Yeah, this is the
Okay.
one.
So your configure, you should add first convection diffusion application. So your configure, you have all the application you compile. Okay. For sure, you have the linear solver application. You might have the structure. You can leave it, but we need these two, the one that are not commented, the convection diffusion application. So just like copy this part and add the convection diffusion application. You have both IGA and convection. Perfect. You're fine. You have both. We need these two applications.
So EGA and convection.
Yes.
But is it in the configure or in the standard configure?
Might be the standard configure. Depends. You compile the standard configure. Yeah, I think it's standard.
Well,
So you have both. You have both IGA and convection.
Yeah.
Fine. Oh, you have all of them. Okay. Yeah, you have the IGA. Okay. It's okay. It's super heavy when you compile, but even like that. Okay. So you have IGA. Okay. Very good. Then we are gonna create. Yeah.
No need to rewrite here.
No, if you have, then we will run, but it will be very fast.
So it's compiled.
It's compiled. Then we compile because we are adding some, but it's gonna be very fast, especially on your computer.
Ricky, how do you call C++? It's hashtag?
Not your pass with
Double slash.
double slash. Okay. Now go back on the folder you have download. This is the folder you have download. There should be 4 files. No? Do you have these 4 files? Yeah. These are elements, and because the objective we are gonna do today, we are gonna solve a diffusion equation. Okay, a simple diffusion equation where we know the shape boundary condition. So we're gonna solve just this equation. Okay, and we are gonna in Kratos. We are gonna create a Laplacian element, Laplacian IGA element, and for the boundary a condition. Okay, so for the boundary condition, we create a condition, and for integrating the area, because we will have a simple square, this will be our omega, with this is the boundary of omega. So for the, we will have our not span. We will have, as Ricky told you, we will have some Gauss point for the area, and we will have some Gauss point for integrating the boundary, because yeah, we will see in soon we will derive the weak formulation, and each term we have to add to Kratos, but we will do it soon. First, let's compile so that we have time to. Okay, so we have just to first we have to bring the Laplacian. Let's figure the Laplacian element, okay, the IGA and sorry, the dot H and the dot CPP of the element, and we will have to put it in Kratos. So application. Yeah. IGA application. Okay.
Can I copy paste through the visual?
Yes, yes. You can.
Yeah, you can. Yeah, like a command C. Costume elements. So we copy and we put it here. I have already done it, but I will show you the element. The .cpp and .h, we copy it and we put it in IG application, costume elements. We put it there, okay? You open the Kratos, no? Kratos? No, application. IG application and
Because the menu is yeah, and then you have to copy the yeah.
Did you manage? Check together. Did you manage? Okay.
We are very strong.
Okay. Now, since you are, do the same with the conditions. So take the other .h and .cpp and put it in costume conditions. Yeah, we'll put it in costume conditions. So. No. In a second, we have to, because it's not so straightforward, we have to do some stuff. We have to register the element and register the condition. To no, I have a mistake. Exactly, and then we take the two conditions, okay, and we put them not in costume element but in costume condition. Okay, mine are here. So we put elements where the elements are supposed to be, and condition where condition is supposed to be.
Did you run the demonstration?
No, not yet. But put the elements and the condition.
Then,
Yeah. Did you put also the conditions? Okay, run. And there is fine there. Did you put both the elements in the costume elements and condition in costume conditions? Very good. Okay, so now we should have our condition in costume condition and elements in costume. Well, now let's go to. Okay, now we have to register the elements and the condition. So command P again. So Control P, sorry, and we go to IGA application.cpp. Okay, application. Okay, we will open both .h and .cpp. Okay, so let's open both. So here I have my on top. Let's close everything. IGA.cpp and IGA application.h. Okay, we have the same. Okay. Now you see, let's go on top. We see that here we are importing the IGA elements that Ricky was. Okay, and then we see that we are registering those elements. Okay, so we have to put also here our Laplacian IGA elements and the condition. Okay, so here first of all we will do almost the same. So include custom elements, our elements. So Laplacian underscore IGA.
Now we are on the eight. Or the
Let's CPP. CPP.
CP or H?
No,
No, no, that
Ah, in dot H. Sorry, dot H. Sorry.
Okay, so what's the general between these two files? What is the?
IGA have all the dependencies.
What are the differences?
Dot H have all the dependencies. So let's say all the other codes you're calling from the character. Is it okay?
Yeah. You know better than me, so.
I know the CPP.
That's the implementation.
Okay, you have the structure of the functions names.
Okay, so it's called
What's Laplacian? What's the name?
it's the name of the file and is the same as you have. Okay, Laplacian IGA element. Yeah, we can put IGA in capital letter, but it should be the same. Okay. No, we capital letter. Otherwise, it's okay. So here we are importing this element. Okay, this dot H. Okay. After done this, we have to do the same with the condition. So also here we will copy and paste, and instead of support regions, we will upload our condition that the name was support. Let's write together. Support penalty Laplacian condition.
So we create a new element.
Okay. Yeah, I didn't tell you. We will set the boundary condition with a weak approach using a penalty. But we will.
Just the short comment. The thing is that we are not able to use the existing support penalty supported because it's designed for structural mechanics.
Yeah. Every time we.
I mean, you see that we have the existing support penalty, support feature, support lagans. Why we don't use that? Because it's designed for the structural mechanics part,
Yeah.
not Laplacian.
It's like simple convection diffusion problem.
So you have to create different files for this specific problem.
Yeah.
Which is not structured.
Suppose you invent a new application like fluid dynamics that is not present in IGA yet. You can create your element, your conditions, and starting from, you will see in few minutes that the element you have just imported is very similar to the structural element.
But here in a way you have as well the collision, because you have to decide which application you have to put your implementation.
Yes.
Either in the convection diffusion or in IDA.
Yeah,
This is something
exactly.
that we have apps.
Yeah, we don't have to care. Ricardo with it. Yeah. Okay, so now let's go down. And also here we have to do the same. It's a bit mechanical, but you see here they are defining the element. So we will do the same. And instead of shell 5p element, we use our element. That is Laplacian IGA element. Copy paste also here. M Laplacian IGA element. So it's just a technical stuff for Kratos, okay? So we have to add this line. Okay.
Then is
Yeah, M is exactly as you see the line before. You see these are all elements of IGA. You see that's element M. That's element. I personally don't know what does it mean. I just learned. It's just I just started as you, just a way to start to do things with Kratos. Then with years, I think, talking with Ricky, with your professor, you will learn why, maybe Charlie also, you can ask, not to me in this case, okay? So same for the condition, okay? Here we're defining all the conditions. Our condition is called support, penalty, Laplacian condition. And again, M and the same. Support, penalty, Laplacian condition. All good so far? Yeah, yeah.
Okay, question. The file that you already have on GECKO, and then we copied and pasted, like all the files that we're working with now. Where did you get them initially from? Did you write them?
I
Code
wrote them.
previously?
Yeah, I put it previously, yeah.
In C++.
Yeah, and okay. But we will go through later. Just to
Ah.
put everything here while compiling, we will talk. We will explain.
Oh,
Okay.
So basically the thing here is what basically.
okay.
Yeah. it's-
So you made it from scratch?
Yes.
Exactly. Exactly.
Oh,
Okay. So we are done for the .h. Let's go to the CPP, and we have to do very similar stuff. So in the eager applications of CPP, you see here we are registering all the elements. Wherever you want, you can copy an element of Ricky, and instead of shell 5p element, we write our element. That is Laplacian eager element. Okay, so I add this.
Did you add or did you delete the file?
No, I add. I didn't delete nothing. No, don't delete nothing. No. Just add a new element. Okay, I just first copy these two lines, paste, and then change just the name. Okay, because all the nomenclature, it's a class that derived from the class element. The geometry type is.
Was there a specific reason why it's
No. You can put wherever you want.
The order doesn't matter.
Okay.
The order is just registered. Okay. Yeah.
Spend on four.
Okay. Then we will come back. If you go down, you have to do the same with the condition. Yeah, this is always the same name. Just it's all the same as the other element, but we just change this name. Okay.
And it's support, penalty, Laplacian
Yeah.
condition.
Now with the condition. Yeah. Sorry. Yeah. Here we see all the elements are registered, so we copy again, and we write our Laplacian eager element. And again, you can copy and write that. Okay, also here, Laplacian eager element.
So where's that, Nicolo?
Yeah, in the register element, yeah. And also register condition here, same. So we copy this. Wherever you want, it's not the order. It doesn't matter the order. So here,
This is after the support penalty class and condition, what we do? We go to condition.
yeah, you have to register in the in the .cpp. You have to register your element. So just copy and paste the one of before and change the name. Yeah, you can see my modification with the green. This is a GitHub stuff. It's very useful. So you can see the line I add. So this I add this two line and this two line. So I'm here.
So that's what you have modified.
Yeah, what I have modified. So yes, watch out also here. Register your condition, and then we are done with this technical stuff.
Penalty, Laplacian condition.
Yeah, it's always the same name. Yeah. No, this is too big. Sorry. Okay.
could you go up a little bit?
Yeah.
No, in the same one, fine, yes. More?
Here. Wherever you want, you have copy and paste and just change this name.
You just added the Laplacian element, you didn't add the condition.
You're right. I have the condition.
Yes. Well, you should.
I forgot.
Ah.
Thank you. Yeah. So here, yeah. So we have to do the same with the condition as what we said. So again here, support, penalty, appellation, condition, typo. Okay. Yeah, no. Thanks to Visual Studio, I didn't. Okay, so we have noticed the elements and the condition. And now we should be able to compile Kratos because we have changed this CPP and .h, the C++ part of Kratos. We have to, you can do it directly if you can go terminal, open your terminal directly here if you want, or you can open a terminal wherever you want. Go in your Kratos. Okay, in Kratos you have scripts, and then scripts, and then launch your configure file. Mine is called configure.sh. Your is Lucas standard configure. Your is underscore Mac, I guess. Okay, so launch your configure. For Windows, it's something else.
So we have done the elements, conditions, now
We are compiling Kratos.
we're compiling.
Okay, so it's mine, and see if there are.
Standard until this call.
The defense is the one that you use because there are others. After that, you see, I hope no mistake. There might be mistakes. Let's see.
It's
Kratos and then saves, and then your configure. And maybe for you it's bad. No, it's bad.
Where is your
Yeah.
So
Yeah, you did this.
basically you have to run this one. That's
Yeah,
basically.
no, maybe it's bad.
You need to recompile from this.
But I don't know if I'm with.
It's okay, I mean, you can put it here.
Remember where
Standard configure is
it's like which commands you here it is. But we can change or like you
So what you
maybe
need to do is finish.
dot slash
The thing is that just recompile.
maybe Ricky, you come here because he has a Windows and I don't remember.
So it's from the BIOS.
I do. Is it working here? Yeah.
There was a typo, but I think it will.
Yeah. Okay, if you see I'm finishing, it's pretty fast because I just change a little bit of color. You don't change too much. To you, it's mobile.
I'm comparing the
So it will take 20 minutes, but no problem. No, now we don't usually need it. So I think SH.
Nico, how
Yeah,
do we
you
run?
compile always with SH. Yes, SH standard Mac.
I have some errors.
You might have done
Obviously, you use this one.
a typo or something. Oh, Lucas, for you,
It's not bad thinking.
Yeah, sometimes this does not.
Kratos, yeah, Kratos is
Also, you use.
Yeah, I did.
I told you this is the manual.
So it's
Yeah.
thing.
yes.
Yes,
you read go on the
They still can't. Okay, you are not like it's English. I mean, I don't know if it's tendency.
yeah, but
I actually
there
want
was
to.
two here.
I don't know what ironic because it looks like it's really fun, but I think it's super nice.
The other one, you see,
No, it's so one-on-one. It's like,
it works very good.
currency maybe is less than the right meaning of this. I thought it was so really. No, there was red. That's good for one. I didn't take the control. Nicolo,
Hey,
can you come? One thing. it should look like a compile.
Yeah,
But then it's in the end of like this image and stuff, you know.
no problem. Actually, but if it 100% it works. Might be some useless stuff, but sometimes it happens. To you, it's working?
Yes.
Very good.
The integrated analytic block.
Huh?
Integrated analytic block.
Ah, okay. We have to do on the front. Okay. Okay. All good here, yes, and there, yes. Very good. Amazing. I like. Okay, so now let's see what there is in the in the condition and in the element, and why is there. So this is our equation. Suppose this is like a temperature. U is your temperature. It's a scalar unknown. Okay. So you know we do the quick formulation. So we integrate our equation times a test function. It's like the principle of the virtual work. Okay, so we integrate f scalar b. Okay, b is our test function. Already be in our space. Okay, you're all familiar with this. Yes. Okay. Very good. So we integrate by parts this, and what we get at the end is sorry. The equation is the minus here. This is the equation, so we have a minus here. So this is the integral over the domain. So at the end, what we have is minus integral over omega of gradient u scalar gradient b plus the term that comes from the integration by parts. So the integral over the boundary of test function times gradient u scalar the normal.
It's minus Laplacian u.
Yeah. The equation was always that. Okay, so and here same integral over omega f b. Okay. Okay. To impose, I can write bigger, please. Yeah. Okay, then we have to impose the shape boundary condition. So we can simply use a penalty. Actually, it's not a penalty. It's a niche approach. Okay. So we add to this. Sorry, let me add it here. These two terms, the integral over the boundary of gradient v scalar n times u minus ud and the penalty term. Yeah, please come. Yeah, sorry, sir. I think. If you are, it's here. If you want, so okay. So these two terms, do I have a color? Okay. I have added this term, Nietzsche approach. Okay, is only to impose the boundary condition, the division boundary condition. So you see here we have this difference. So we are enforcing at the boundary that u is equal to ud, because this is, remember, is for every test function in our space. So we will have to add these two terms. Okay, this is our formulation, and this is equal to that one, integral omega f. Okay. Okay. So we will have two contributions. on omega, okay, we have this contribution on omega, you see, and also this contribution will go to omega. So this contribution will go in the element, what we call element. So on the Gauss point, on this Gauss point, on the element Gauss point. Instead, this contribution is over the boundary, and also all this contribution over the boundary. This will go in the condition. And will be all this point. It will be a lot of, okay, this is the condition. And yeah. I made a mistake.
No, that's because I don't know. Maybe if you write on the
Yeah.
Really, I think it's because you're too far, because.
I can see it.
Thank you, Lucas.
No, I mean, that's smaller.
Okay, this is I think it's something that you have already done in your studies a bit, some of you. But yeah, and instead this is in according to what Ricky told you before. So we have in Kratos we have elements that actually are integration point for volume or area. Okay.
But let's say in this case, the whole set of four integration points is one element, or each integration point is one element.
Each integration point is one element. So we will see then that our don't stay here. It's just Control P, Laplacian, Iga element. Okay, this is this is doing something that we will go through. This is my no, not this one. Yeah, sorry. So Laplace IGA element. This one. Okay, this is what we are using. This is one Gauss. For every Gauss point, the code will enter here and will assemble the contribution of that Gauss point. Okay. So we expect to have in this Laplacian Iga element the implementation for adding this term and this term. Instead, in the condition, we are supposed to implement the green terms. Okay.
Could you repeat?
Yeah. The last part. So we have two different types of Gauss point: the boundary Gauss point and the internal Gauss point. The internal of each Knox point. Okay. The boundary Gauss point are used for this integration on the boundary. You see. Instead, when we have to integrate over an off span, okay, or a volume or an area, we use those Gauss points. Okay. Yeah. So now, okay. Now let's see in the code. It's just I will not touch nothing. So let's see the Laplacian IJ element. So the one we will use in few minutes to see some examples. Okay, these are all stuff that I have just copy and paste. Okay, from the classical Laplacian element or graph element. Just stuff that I read. I didn't get perfectly everything, but yes, I'm just I think it's pretty normal to don't understand everything, but start to do something, see,
So
then
the
ask
thing-
questions.
The thing is that in Kratos, we have template for the elements, I think, of something, you see, I mean, important components like constructor, destructor, and so on. So you just need to I would say, to copy that template and fill the necessary functions that you need.
Yeah, for example, here is where it will enter for each Gauss point internal or for integrating a knot span. Okay. Okay. This is, as we have said, element is one of these knot points. Okay. And for each of those integration points, we will enter here.
So you calculate the left-hand side and the right-hand side for the internal
For,
quadratic point.
yeah, for that contribution, that will have a weight, okay? And that weight will be we can think about it as a little piece of integration, okay? You can think it's not exactly like that, but you can think that this integration point is taking this contribution, okay?
So
This
okay.
okay, you can just think like, okay,
So you're using a weight for taking into account that area.
that yeah, at the end, yes, okay, yeah.
So it's an additional weight in addition to the quadratic weight.
Yeah, yes,
So you have
it's built on top.
multiplication of two weights, let's say.
You make it that it's the mapping between the physical and particle space, and the determinant of Jacobian is the area. Like you remember that one.
Yeah.
That's the determines the area.
Yeah. Okay, so here we can see we get the name of the variable we are using, that is temperature in this case, because it's a diffusion problem. So we have conductivity, the heat flux, that is our F. Okay, call heat flux is a bit confusing, but it's our F, our forcing. And yeah, here, for example, we compute the derivatives, because here we will have to integrate this here, no? The gradient of the basis function, because you wanna explain that part.
If you want,
I think you can explain that. Yeah, and then I will explain. He knows more. So you explain from just for like one term. Take the first term and write with n. Yes.
okay. Okay, basically, you know that okay, in classical term, but also in GA, we express
Maybe with the
yeah.
oh, you want right? Yeah.
Yeah, it's the
Yeah.
same.
Like this.
Yeah. Okay, we express our unknown, I mean our u. I don't have a very good
I
calligraphy.
really
so-
like your handwriting, Nicole.
Thanks.
Yeah, you won't like mine. We express our solution in terms of a linear combination of basis functions, okay, times some coefficients. Okay, this is our solution function, okay, in the space. So let's say C, with C, I mean, we have our domain in X, Y, physical domain, and our parameter space, all right, parameter space in C eta, okay. Let's say that I will call just X the set of physical coordinates and C the set of parameter coordinates. So U in the parameter space is just the linear combination of our basis functions that are defined in the parameter space times some coefficients. Okay. Is it clear? It's exactly the same what you do usually in France. So now we have to rewrite this formulation using basically substituting what we just said. So U is just a linear combination of all these basis functions, and we are testing these equations against some test functions that again are taken from the same space. In the sense, V is a general function described as another linear combination of these basis functions.
Maybe usually I and J for
Yeah.
one and J for the other.
Okay, so
Let's use J for U and I for V. Because then those will be the row and the columns of our final linear system. Okay, because at the end the Uj are this one. This is a vector U1, U2, and so on. UN, which are the solution of our problem, and will be the value of the DOF and the contour points. Okay, they will not, because
Yeah,
in ITA,
it's not exactly true, but they are.
the value of the DOF is not the value of the solution at the contour points. Yeah. That U is this U. Okay, that we want to solve, to obtain.
Basically, when we say that we want a solution U, we want the coefficients Uj. Okay, because when we have the coefficients, we can do the linear combination, and we can compute the solution in every point of the parameter space. Then we can map it to the physical, but starting from the parameter space. We want to test this against each test function. There is each general linear combination, but since V is a general linear combination of this basis function, it is sufficient to test this equation against each of the basis function. Okay, so V basically it's in the, I don't know if you're familiar with this notation. Okay, I don't know, and 0, 1. It's a general function that derives as linear combination of this. Okay, so what we want to do is, I don't know if I have enough space.
Yeah, we can come here. Oh, no,
Well, I mean,
you can start something.
No, I think that they already ordered. Okay, here we write again this, substitute here the linear combination. So here we have the integration of our domain of the gradient of U, that is just summation over J and J. Okay, let me write just the first time because it's the same for all the others. Okay, so I'm writing only this one. Okay, what we do now, as I said, to test for all the test functions, we just test for each of the basis functions. Okay, so basically, these BI are just the coefficient to create a general test function. We don't need them.
They are arbitrary.
Yes, they are arbitrary. We just have to repeat this computation for all the test functions I. Okay, so each of the basis function we will create one condition. There is one row in our linear system. Okay, so basically this is for test function B equal and it's the ith row.
Yeah, this is in general for FEM also.
Yeah,
it's
this is
not,
in general for fun. Okay, so the higher the rows, we want to compute the J. Okay, so let's say if this is the formulation of our final problem. So we have a matrix times our unknowns equal to B that we derive from the forcing term, and these are U1, UN. Okay, basically the columns describes our coefficients in the sense that this term here is a term in the first equation, so tested against the first basis function that is n1, okay, and correlated to the first unknown u1. So to understand what goes in here, we just have to say, okay, each uj is correlated to it's simple. We just have to move out the summation here. Okay, let me do this and then I'll explain.
Something important to remark, which is a difference with classical FEM, is that in classical FEM, you impose strongly
yes,
that if the condition you wouldn't calculate, because let's say the second term will be for calculating the reactions
Yes.
in the post-processing.
Yeah, exactly. Yeah, this is a weak approach to impose the initial boundary condition. That is the niche. Yeah, if you in FEM, you usually don't impose it weakly. You can impose it directly strongly because the basis function in the nodes are one in the FEM in LGA node, so we cannot. So
And the nodes belong to the geometry.
also. Okay, basically, if we take the summation over J out of the integral, okay, the gradient is linear, so we can do it. We can do it. So this is UJ. Okay. Okay, just put the coefficients UJ at the right side of the square bracket, because this is just a coefficient, so we can take him out from the derivatives and integrals and everything. Okay, you can see that this is basically each term that multiplies each coefficient uj. So basically, if we put if here we don't do the summation, we have for each j, in a sense, we have the position on the jth column. Okay, so basically, this summation is just doing the product row by the vector unknowns. Okay.
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 No, I think because we have a few times.
Okay. Just that thing that's important. This is integrated over the physical domain. Okay, but the basis functions are evaluated over the parameter space, so we can't evaluate them directly. We can't, for example, compute the Gauss point in the physical domain because the element is distorted. It's not so straightforward. So we have to map this integral to the parameter space. Okay, so basically we end up with, I will write like this. Okay, this is the parameter space. Okay, and it will appear a term Jacobian, determinant of the Jacobian. Okay, and then we are able to compute the values of the Gaussian point. Okay, without writing it explicitly, but that's the procedure. So you move to the parameter space and then you compute whatever you want.
Okay.
Yeah. So part that you will have mi times vi,
Where?
or j, whatever, and you have, right? Yeah, and you remove the v, the test function.
Yeah,
because
So this is like because it's arbitrary,
yeah,
and
exactly.
because the arbitrariness imposes it should be all 0 or something. It's like an equivalent step.
Yeah,
Yeah.
yeah. The fact is that it's a test function. V is a test
It's a test
function.
function.
Should value for every test function. So
So
vi, we can simply at the end can simplify the right, because it's also in the right. It's in both sides. It's also v. It's also on the right
Yeah,
side.
so-
So we can simplify
Yeah,
them.
you can remove it, and it's in the beginning, and then you say this is arbitrary because it multiplies, it should be 0. Whatever multiply, because it's arbitrary, whatever multiplies is 0. So it's the equivalent step at the end, right?
yeah,
Yeah.
it's the same as doing this here.
This is how you remove it. And then what is the difference? What is the, because up until this point is exactly the same.
It's not. It's still
No,
exactly the same.
exactly the same.
But-
The only difference.
But I thought then you said something about the physical space and the
Yeah,
parameter space.
here.
But before that is something also different.
No,
No.
no.
Up to here is exactly the same.
Straightforward. Yeah. Exactly the same. Yeah.
So parameter space, I mean, the IJ framework simply means that the basis functions cannot be evaluated in the
Yeah,
physical.
it's in another space. So
Yeah, so you have to map it to the parameter, to the Jacobian, and yeah, you also have actually
But
also
also
this
for-
gradient are in the physical, so you have to yeah multiply the derivatives in the parameter space times the Jacobian to.
But before that also one comment. You made a comment, right?
What I comment is that let's say you are constructing the test function as a linear combination of the basis function, the net basis function, times some arbitrary coefficients. Those arbitrary coefficients allow you to construct the matrix form.
Yeah, I mean, it's okay.
Let's say
How you go
the
from-
VIs are arbitrary.
Yeah. Okay.
Yeah.
But is this like a difference between AGA left?
No,
Is
it's the
this
same.
the
It's the same.
Okay.
When you standard IGA, after that step, you use the elements.
Yeah, you
You
map
use
the parameter space and you create the Gauss, because the Gaussian point are in the parameter space, and you can also think about the Gaussian space, but okay. And we use that to integrate because there we know it. Yeah.
Okay. Let me write one last thing because sorry. Okay, basically, this is the time we want to compute in the end.
Yeah, this is one I wanna exactly.
You want to explain?
No, just to show in the code.
Okay. Just to say why we can summate over the Gaussian point. Okay. I said that we were going to do it in the parameter space. So here we have the Jacobian. Okay. Actually, what we do is that we describe this as the summation over the knot span. Okay, because you know that the parameter space is just subdivided in knot span. Okay, so we describe this integral as the summation over the integral of each knot span. Okay, of the same thing, and then we can redescribe it as a summation over each knot span. I mean, each of these integral can be evaluated through Gaussian point. So here you have again summation over Gaussian point, and all of these evaluated at each Gaussian point times.
So in the end, that's why you can define an element as a quadratic.
Exactly.
So you are describing the extra loop.
Yeah,
That's the numerical integration.
yes.
So in the end, you can simply do one summation over each Gaussian point.
Yeah, a big summation of it.
Yeah.
Yes, there is no point of looping into an element and then looping.
Exactly. It's a big loop
Because
over
it's
all
just
the
a
Gauss
summation.
point.
It's just a summation in the end. You don't care about
Yeah.
the individual
So
Yeah.
subgroups.
Yeah.
You have to
Exactly.
see when you consider a specific Gaussian point, which are the basis functions which are not zero at the Gaussian point.
Very good.
Can you repeat this?
So you will loop, let's say in the final program, you will loop over all the Gaussian points, which are the elements. So at that element, you have to consider which are the basis functions which are not zero at that element. Because those are the contributions you will have in the global snippets matrix.
Otherwise, you should go over all the basis functions. That's not so
You get it?
leave the support.
Okay, so you need to know which of
And
them.
that's the local support of the basis function.
Tell me, Kim. Your question? Okay. Let's go further because I have.
But there's also an unknown.
And
The
yeah, the values of the basis function.
I mean the IEN.
What?
IEN. That
What
when you
that?
have the elements, you know which are
theory.
the basis function, which basis functions are supported in that element.
Yeah.
As
You
a
have it stored. So
Yeah, of course. It's yeah.
extracts container of.
Yeah, they are contained.
Has
Yeah.
this
But
information.
let's go. This we can discuss in the break, but we are still. If you agree, we can finish at 1 because now it's just
Okay.
we will run like our the scripts and we will see some results. So it's just a game. It's nothing theoretical. Okay. So you can go back on your computer because now we go on the code. Just very quick, we go through the Laplacian IGA element implementation. It's very, in my opinion, like a badly code. So you can at home you can use it as a reference, but it's not super efficient. It's not optimal. I define multiple times some stuff, so it's not. But it's something that at least you can start on. And I think it's pretty intuitive. So, for example, here we have our weight of our integration point. Okay, so integration point dot weight. We have the 157.
With the code actually.
This is Laplacian IJ element dot CPP. So this is one Gauss point of the area. Okay. Yeah. So here you see there is the absolute value of the determinant of the Jacobian for the transformation from physical to parameter. And for example, here I'm summing the left hand side. So here I'm actually taking the contribution of this Gaussian Gaussian point and pass it to another place in Kratos in order to sum this local contribution to the global the linear system. And you see that
the builder and solver.
yeah, in the builder and solver they do this. Yeah, in the builder and solver they call this element. Every of the days they loop over all these Gauss points. Okay, and you see here we have this term that is exactly this term, the gradient of n times scalar product, the gradient of n and j, and exactly okay. So I'm summing to the left hand side because we are on the left hand side this term. Okay, but you can go through more in details by your own. And for example, in the right hand side instead, you see I have the same as there also here in integral over omega. F, yeah, F is how it's called it flux local, and you see we are doing n times F because yeah we have also here we have write F as the summation over I of Vi and I. No, we simplify the Vi as the corresponding, so at the end we have Ni times F. Here that's why we have n times F. Okay, but you can go through, and if you have a question, just ask me. In the future, we can do a Zoom meeting and go through the code. Okay. The same we have for the condition. So go on the CPP support penalty partial.cpp. Okay. In the .h there is nothing. There is just the import stuff, but the main part is on the CPP. And as I was saying before, the condition is one Gauss point on the boundary. Okay, element one Gauss point internal for integrating a volume of an area. This for integrating a boundary term. So
Condition is like boundary.
boundary is exactly is for these three terms, and we will see that I'm adding three terms. Exactly those three terms.
Sorry, I have one question.
Yeah.
The boundary terms, when you are considering the quadrature points, the Ni are the one corresponding to the trimming curves.
Yes. Yeah. Yes.
Is that way already?
What's the question?
When you're evaluating the boundary terms, and you have, for example, you have nabla b. Those basis function you're using there are the basis function from the boundary representation.
Exactly. Yeah,
So from the trimming curve.
Yeah. Of course, the component is there. At the beginning, we designed the Gauss point on the boundary, and we evaluate all the basis functions there. So here they are available. Okay. Yeah, but
This is quite advanced, but this is what we call PREP curve on surface because these underlie on surface.
Okay.
Yeah. For example, in the implementation of the condition, you can see that I need the normal the normal because here we see the normal, so I will need the normal. I need again the gradient because the gradient of n, because here there is the gradient of n, and here there will be n, and the boundary condition. So normal parameter space, I calculate it here.
And then there is a method for Kratos to calculate the normal.
Yeah, there are
So you don't
some.
have to really implement it.
No.
I mean,
There are different ways.
it's located in the geometry.
Yeah. So here you see I'm adding the three terms on to the left hand side. You see, h is n. Okay, just h is n. So you see here I do depend. This is the term with the penalty. So we term with alpha. This is our penalty. You see, I do n times n because there is v and u, no derivatives. So you see h times h. The second term, I wrote assembly of the integration by parts term. So v grad u scalar n. So it's this one. This one. Okay, v grad u scalar n. This term, and I have sum up his contribution here. Okay, so I have n dot the term that this term. Okay, I have just built all the terms and some.
And you are calling the basis function h.
Yeah, in this case, okay. Yeah, it's a bit confusing. Sorry. And then the last term. So I see I put all the three terms, and you will have this code. So if you need something similar, you can maybe start from these and maybe add terms.
For example, for calculating the determinant of the Jacobian. what do you do?
It's up on this code. It's already implemented. You can just call the Jacobian and you will have it. Yeah. Okay. Yeah. You can check in this code. You can actually the purpose of this is to have an easy code because it's it's just the temperature is just it's the simplest equation. So it's something easy that you can start with.
Later we will do some optimization of that one. Just one demonstration.
Yeah, and then here I have also the right hand side of this. You see here I have UD, our value that we want to impose weekly. Okay, so I have moved the term minus UD to the right hand side because it's known. Okay, and so I add it also there.
And in this code, you're not applying the SVM.
No, this code no.
Not in this code.
No, we will not.
In another code.
Another code, yeah. I actually, yes, it's another condition. Okay, then we can discuss, but I think we will have time maybe later. Maybe
Let's see.
if I have 10 minutes, I can explain the idea.
You are modifying the weak form.
Yes, yeah, I'm adding another term to the weak form. That is not on the external boundary, but on an internal boundary. Yeah. So it's another condition with other Gauss point. Yeah.
So it's not so difficult to modify the code.
No. It's actually, yeah, it's very good Kratos because you can add few stuff and keep all the same in the rest. This is the beauty of Kratos. Okay, so we are ready to run our code. So let's go on the other Visual Studio page where we have opened the folder, the trial IGA basics. And if Kratos has compiled without any error, sorry, I forgot. There is another stuff because I don't know it's not working. You have to open search for convection diffusion solver.py. Okay, so command P or Control P in the Kratos folder. Do Control P and write convection diffusion solver.py. And we have to comment these two lines because it's convection diffusion doesn't agree with it's something that Ruben needs to manage because convection diffusion so far it was for FEM, so they are not dealing with strange entity like NOSPAN, so it's just a check, and we are just commenting these two checks. You see the blue, you have to comment these two lines.
Line 320.
Yeah, I hope it's the same for you. Might be not the same.
Replace element.
Yeah, replace element and condition process. Yes, 320 and 329. Comment. With comment, you just put hashtag.
Yeah. Why are we doing this?
Because just some bugs. These are checks replacing condition process because Kratos is made for FEM mainly, and they have to manage that we have other entities because now as I told you, one Gauss point is one element. They were used to one element needs nodes, but I don't want nodes. I have just 1 point. So just but yes.
So just comment this line.
Just comment this two line and compile again. So
Which line?
320 and 329. 14 is okay. Yeah.
Like it's not in your code.
No, solver. No, solver. I think it's the first one. No. Yeah.
That you replace elements with condition process.
Yes, and also 329.
Standard configure.
But this is just one.
Okay.
Okay.
1.9.
20 and 29.
And did you find this
When did you have that?
or Ruben?
No, because when I run, I saw that the code was like a stuck in here. There was an error, and I went to ask Ruben what the fuck is this, and I told him, no, okay, just comment for the moment, and then in the future we will solve it.
Why do we need to compile?
I am not sure because
It's checking the element positions.
No.
It's,
the question is why we have to compile. If we will modify a Python,
it's only the
okay, maybe we don't need. For mine,
It's a Python.
It's
no?
Python, we don't need it.
yeah, I know, but
I mean, I don't know, maybe we.
No, we don't need it. We just, we can pause it, I mean.
yeah. Okay, so let's see if it's not working. You have to
Then I
compile.
compile. Okay.
Okay, so going the other where you have where we will run our main Python. So just look at our main Python we have. Are you all at this point?
So we are inside the scripts folder.
Yeah, now on the other one, yeah.
Yeah.
Where we, just notice that
Your folder.
yeah, my group, yes, on my folder we will launch a simulation. You are at this point, Kim, okay? Pritimi and Joan.
You have to go run.
No. Okay, now go on the folder on the folder you have downloaded, and let's open the Kratos main IGA Nico. Okay, and you see here we are using the convection diffusion application. So convection diffusion analysis is a class that is derived from analysis stage. So we are always using the analysis stage, and yeah. Okay, so of course we have the geometry.cat.json, we have the physics, we have the material.json, we have the project parameter refinements and so on. Just look at the physics, the physics.iga.json. Okay, you see, I'm calling my element, Laplacian IGA element. I'm not calling 3D shell, okay? Physics. The physics.iga.json. We are calling our element we've created, and in the condition, we are using support penalty Laplacian condition, okay? Otherwise, we have to set the condition, okay? Let's try to run. So, Python 3, Kratos.py. It might fail for you. Maybe you need some Python.
Yeah.
Okay, to me it worked. Python 3, and then the name of Kratos. And that for you is working. Can you check, because they probably have to install maybe NumPy or something.
It says no module name.
Yeah, are you using it?
It's in another before.
You are in which folder? Yes.
Maybe it has an
Yeah, exactly. If you tab, Kratos,
okay, yeah. Nicolo.
maybe it's like a Python 3.
What?
If you,
Yeah, I know.
yes. Python was not found. Yeah, go on the normal terminal. Yeah, you can run it also on the normal terminal. And then it's working.
I have to rerun your commands.
Yeah.
Can you explain
Every
what
time
you
you open the terminal, you have to export. You have to export where is Kratos to Python. And otherwise, Python run and you write at the beginning of the Python. So you say that you want Kratos to
you cannot find
they
it.
say, I don't know where it's Kratos.
So this command.
Export Kratos to Python.
I think it's. Yeah.
It didn't run by two.
Yeah, I think it's the same.
So you have to combine it.
Let's say
Combine, yeah. Because you will find the Python, you will combine. Combine and then you return. Yeah, it might be that you have to combine two. I was
I'm using
But why?
Then, because, actually,
I mean, I think so, because it's giving us an
yeah, for sure. So go back.
yeah,
combine.
one time step, no? Yeah, now, so
Yes.
combining.
No, that's me.
not that.
Okay, for the one that is working, then we go back. So for Andrea and Kim, no.
My case, I got one time around.
For Python, you combine again.
After the change that we need to the compare.
No. Oh. No, you always combine. You're using a different Kratos because it does not really.
Okay.
Yeah,
Yeah, combining and the main Kratos.
you can do it for
I don't have much yeah, but you use okay.
You can, he does not have much for, he just do like a fifty star. You don't have that? Just do 50 star. Yeah, because, I
Also here, there's no matter B.
do 50 star, the math profit. No, because we need it also for
Yeah, yeah.
synchronize the results. Do you have keep, try to,
It's not why.
for why is, for the ones that is working, try to launch the post process. So try it, now we go back for Andreas.
It's in the same.
Yeah. It's like a homemade post process where you should see something.
Made by you.
Homemade, not made.
So it's gonna read off the city.
Yeah, it's starting of views and yeah, okay. Very good picture. If you run, you should see this. I mean,
So Simpa is like
do PP start
Simple
CP.
CP.
Yeah,
it's done.
yeah. Like probably all of you don't have maybe NumPy or SymPy, just start.
That's not possible.
Process.
I was installing math.b.
Okay.
Yeah.
Try Python 3
Wait,
working.
what do you use the
Those process.
oh what is it?
Yeah, it's good.
No.
It works, not yet.
Nico, is my
You know.
you better than
Simple unit.
I use the
This is your thesis.
Yeah.
Now I have your thesis. I'm gonna publish it.
give you like these results.
Continue. It's working. Also the post process. Launch the post process. You probably maybe don't have NumPy. That's try to Python 3 post process.py. It's for like it's in the folder. For on this one, this is working.
Yeah, but we have to install simple.
You have not sure why. This is his file, not my file. I don't know. I asked him.
Oh, incredible. Yeah, I have. Yeah.
That's the web design.
I think it's maybe Windows.
I did it on anyway, like it's already this is going, it's okay, it's good. There is some bug maybe that for Windows, but for them it's working. It might be, it might be not Kratos, but maybe Python for Windows, like NumPy or something.
Because you did it.
Yeah. Anyway, what's this? I might say it doesn't, you don't rewrite everything. What's this? This is okay. Let's go. Let's go on the post process .py to see what I'm doing here. So I'm importing a txt file. Okay. Line 14. Okay. All of you are okay. Okay. Where if you go on txt file, output
output result. You see, I have a bench of data. Okay, I'm just explaining my homemade post process. Okay.
Where did you learn?
Yeah, you see on the left TXT file, output. Okay, I'm just importing this where, and these are the coordinates of the Gauss point, the solution, and the solution. Okay, there are three. Sorry, there are.
Because this is not like the product of what we saw.
Yes, this is the third column are the value.
Or you made this.
No, I mean, the question that
I made this file. I made this file.
But it's after a solution, or it is like
No, at the end.
from pre-processing.
No. It's the solution that that Kratos. I mean, with Kratos, we have created this file. This is an output from Kratos. This is
But
the
we just
solution.
put it in the package, so have it.
Yeah,
Even if we didn't solve it.
no, we did solve it. When
So
you
this
did,
this is if I didn't solve if I hadn't compiled.
no, you would
I
not
wouldn't
have this.
file.
No, you would not have this. Yeah,
Okay, so it's
yeah.
Where did you find it?
TXT file output results.
There's a folder.
Yeah. Okay. So we are just reading the coordinates of the Gauss point, reading the values of the solution at the Gauss point, and plotting them like in a contour plot. You can also go at the end of post process, and if you uncomment this plot show, and you run again the post process, okay, just you should, it's another visualization. Just use here a 3D visualization of your solution. Okay. Oh, come on. Okay. This is the exact solution because we are using an ideal solution. This is the solution we got with Kratos. Okay, you see it. And this is the absolute error. It is 10 to the minus 5. So it's we are now we will see a convergence value also. It's all okay. So and why we got this solution? Okay, because if you go in the parameter.json, try to go in the parameter.json. Try to go in the parameter.json. Here you can see that yes. Here I'm imposing this derivation. These are where I set the value UD. Okay, you know, to import the boundary condition, I have to set this UD. And here where I'm what? Anyway, oh, it's too much. Okay, this is where I impose UD. For example,
So can you repeat what we do to project parameterization?
yeah, if you open it, you can find this line 72, and this is our initial boundary condition. This is the function I'm imposing at the boundary. Okay, in a weak form with the terms we have seen before. Sinus of x times it is something highly non-linear, so that we can do also a convergence study. Indeed, if you run Python 3 convergence, it's called convergence main Kratos.py, it's in the same folder. If you run it, it will run 3 times. It will run 3 simulation with 3. Yeah, it will run 3 simulation with 3 different size of not vectors. Okay, we are doing exactly refinement.
So it implies the refinement.json.
Yeah, in this Python you can read it. I'm just run the simulation with 7 not insertion. You can find it here in the convergence. You see here I'm putting. I'm doing a lot of simulation. 1, 3 with 1 not insertion, with 3, with 7, with 15, and 31.
It's each refinement.
Exactly. And then I call Kratos and I change the input file of Kratos. That's the refinement that is here. I'm just changing this.
In this case, you're using quadratic or linear basis functions.
this case is linear because I'm minus
So you have quadratic conversion.
third order, p plus 1.
And so it's quadratic basis functions.
Sorry. Exactly. Yeah, it's quadratic basis function. Yeah, exactly. If I put 0, it's linear. Yeah, if I put 1, it's quadratic. Yes. This third order convergence, you see, the velocity 3, because I'm using quadratic basis function. Let's change it. Let's go to the refinement and let's put instead of 1, 2. So we are using third order basis function now. Okay.
Where increase degree u to 2.
And also b, because otherwise, yeah, in both directions. Okay. So go on refinement and change this. Now we are changing, instead of using linear basis quadratic, we are using third order. What convergence do we expect with third order? Fourth. So let's run again without compiling anything. Just run the convergence main Kratos again. Here we go. 5 simulation. Will be very quick, I hope. Already done. Fourth order convergence. So yes, okay. If you do, I think I don't know why. Windows.
Yeah, the end error.
Yeah. We should get the fourth order, right?
Yeah. Did you put 2 and 2 here? Yeah. And yeah, to say that twice. Yeah. Okay. And of course, you can also use the 2 and 2. Yeah.
Okay, now. Increase.
If I want to run this here in the terminal,
Why is it for third order? So
Because now it depends on the jump, with what did you do with Rhino. With Rhino, you build the basis one, and my basis one is linear. So if I put 0, it's linear. If I put 1, is you increase by 1. So it depends on what did you do in Rhino.
So in this case,
In this case,
it's third order.
okay. Let's do one thing to check our code. So let's go on the project parameter. Let's go to the project parameter, and okay, so far we were using a highly nonlinear solution, okay, so that we can see convergence. But what if we use a quadratic solution? So let's change our problem. It's the same equation, same differential equation, but we change the boundary condition, okay?
why are you called, sorry?
Yeah. Line 70, we comment the value of sinus of x times sinus hyperbolic of y, and we, for example, let's choose x squared plus y squared. This is the new solution. Of course, we have also to change the forcing f. Okay, forcing f, it will be 4, because if u is x squared plus y squared, the Laplacian of u f must be 4, no? Because it's the second derivative of x plus.
So this is not the Dirichlet. Let's say this is the analytical solution.
Yes.
Ah, okay.
No. This is This is Dirichlet. Yes, it's both, because we are imposing the analytical solution at the boundary, and then Kratos will solve inside. Okay, we're not imposing inside. Okay. So of course, and also here, instead of 0, we put 4, okay? Otherwise, it's not, we are changing f, okay? So we have just to change f and this one, okay? And another thing on convergence, of course, we have to change the exact solution, okay? Because, yeah, also in the post process, okay? So go on convergence.
Can you go back to project parameters, please?
Yes.
Once again.
Too fast.
Yeah. You have to change.
Okay.
Comment.
We change the temperature and then.
We will go to tab.
I have comment the 0 and put 4, because now 4. We are just changing the okay.
Yeah.
Now convergence main Kratos.py, and if you search exact, exact line 84, we have to change. We have to comment line 84, and instead we are using x squared plus y squared. Okay, so they are just changing the exact. I mean, because when you compute the error, we need the exact solution. Right? You cannot route the error. Okay. So after doing this, we can do the convergence again, and well, which function are we using? We are using third order basis function. So when we do the convergence study, it looks weird, but we are 10 to the minus 14, so we get the analytical solution up to the machine precision immediately with one H refinement. This is the fact that the solution is quadratic. We are using third order basis function, so we can obtain the exact solution only like no matter the size of my mesh. Okay. If I use instead linear, so let's put 0 in the refinement. What I will see if I use linear basis function and my solution is quadratic, I cannot capture the exact solution. I will have to refine the grid and get the exact solution. Okay.
So we just change to linear now.
Yeah. Just put 0. Same.
X squared.
Yeah. We have quadratic exact solution, and we are using linear basis function. So this time we will not you see, second order convergence, because we are using linear basis function, and as we expected, now we are not 10 to the minus 14, we are 10 to the minus 3, and we are converging as expected. Okay. And any question? I see.
No, good. Thanks.
Yeah, I'm sorry that for Windows, I don't know why it's not.
Can you explain this image?
Yeah, this is okay. This is a convergence study. So we have the L2 norm of the error on Y. So it's an estimation of the global error of our domain. Okay. That I computed it with the exact solution.
This is like the norm of the error.
It's the norm.
Some way you don't know the mathematics, but somehow you compute the error in general, like average error.
It's kind of an average error, yeah. And here I have H, so I'm refining the grid.
Smaller and smaller.
Yeah, smaller and smaller. You remember I put 1, 3, 5, and so on, and I got some points here, and they are all aligned because it's is working. And you see, as I refine the grid, the error is converging.
So this is double logarithmic.
Yeah, it's log. Yeah, you see, it's log. Yeah.
So
in log, I have second order convergence because I'm using linear basis function. If I increase there, I will get.
Like before. Okay.
Yeah, you can play around. I put there some linear basis function.
But what is different?
That depends on the order of basis function, because this is a bit the theory of M.
Yeah, I've seen these diagrams in like comparing.
Yeah, everybody.
And stuff.
Yeah, because this is how much is reach your test space. It's fine. Okay, if you use quadratic basis function, your space where you set the solution, your approximate solution is much richer, and so you can. Yeah, it's a bit more complicated, but if you go in a FEM theory, it's a classical.
I've seen the similar.
Yeah.
Study.
Okay. Any question? Otherwise, we have to go.
Okay, it's just a stupid question because when we're changing the values for U and V, but what would happen if you change one in Scotch?
We can try. For example, suppose it's very quick. Suppose on U I keep linear, and on V I put not 10. Put 2. So it's third order. which convergence do we expect? Still second order or more? Still second, because, and we can check this, because of course the error on U will be higher. Yeah, it's still second order. Maybe it's something different, but still second order. And maybe if I check the post process of the last iteration, okay, something. No, because no, don't look at this, because of course also in the post process. Yeah, because I was just to what you said. Also in the post process, you have to change the exact solution, of course. I was using the one of before. This is the exact post process. Yeah, and it's something, yes. And this is there. Yeah, okay. So yeah, you can see yeah, this is the exact solution we're using. It's a quadratic, and also the RGA is the same. Yeah. Okay, let's go to lunch, and if you have a question, then I can still answer.
We still have one more session.
Okay, so it's over.
It's over, okay.
Wow.
Because if there's no question.
No question. No, actually, we have to move.
You have a window.
Yeah,
Or Reno, right now. Reno.
So for the next sessions, now we are trying to use Rhino and this plugin to generate the input file for Kratos. So I would like to suggest that you form a group, I think 2 people in one computer.
Yeah. Maybe Ignacio, if you have, because we have only 4 windows. Yeah, exactly. We have to.
What is in there?
It's coming. Like for example, Andrea, Andros, if you can, because there are like too many windows together and 0 there. So
We have one, Philip.
yeah, but me and Laura, we don't have any windows.
Kind of doesn't work.
Yeah, so we do have like either.
Where can I plug my computer?
Here's the outline. Yeah. Like let's. Yeah, you find there.
Hey. No, but because I think.
Yeah. Okay. Sure. All right. Go to
The video that was like when I. But I think it's interesting. Well, I mean, maybe I just want to respect.
By the way, I would like to inform you that you need to download something. I put also in a Google Drive called this local.zip.
Only on the window.
Yes,
Okay.
unfortunately.
What you have to download really?
This one, the first one, crocodilo.zip.
Yeah. Chill ones. You download
The plugin. The plugin.
I want to.
If you already have it, then fine. I mean, this plugin. At the end of the day, you look like it's
No.
You have a. No,
I don't have a license.
you have to go. No, you have to go on the drive and where you have found my folder. There should be crocodilo.zip. And now.
okay. Well, yeah, suppose all of you are already downloaded Crocodilo, and then what you need to do is go either to these tools, options,
One second. Where are we behind here?
Oh, yes.
Sorry.
So-
Meetings.
Yes. I'm trying.
Maybe with the hands.
Do the screen.
No,
No, just
if you-
Like that. In the screen, on the screen. Yeah.
Okay.
yeah, perfect.
Screen.
Thank you.
Where do you go?
So tools,
And you're on the-
options,
you're on the-
plugin. Tools,
Yeah, but
options,
I don't have a
plugin.
license for that.
Oh, this is.
See?
Well, it's a great there. I think there is all of them select something really good.
So I don't think your life should be very long.
Yeah, cool. Well, it's really that it's over. Integrated hygiene is integrated
Ricky, can you explain what is egg position? Because
Yeah, I
we didn't
am.
mention.
I mean, the first thing I would like to have properly installed.
Okay, and then we.
Then we will set
Uh,
options, plugin,
Yeah.
plugin, and yeah, I think I will do it one person by person. This is easier.
Yeah, sorry, because I can see. Well, free and.
We are still-
Rhino, Rhino or Rhino?
Wait, the problem is that.
Yeah.
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 They think that this is kind of virus.
Yeah, what, yeah,
How
Ah, flash hands. Yes.
I mean, I think it's a lot of nice first impression. First impression. Maybe we need to make it professional.
Okay, even continuously.
What do you think of if it's super negative, don't
I will
talk.
talk like that.
Really? But sure, yeah.
Okay, that's fine.
I don't know. But when from the school,
That's confusing. Yeah.
in January or November?
No, I'm like to.
Nice. I didn't think I was giving that impression.
Yes, to get that. So you have to, I will show it to you. Yeah, exactly. I won't explain to you. I just want to make it.
But I think it's an expression like but the inside of like a very yeah. Yeah, you're right. That's like so bad. I mean, I think it's like nice to even if like working with like I think that I did the profession without super like the side of like I try to be I don't know.
But
It's crazy. I wasn't like this could be not like Like not saying the right things, maybe, or that I'm like not saying the right words, or that I'm like getting stuck.
You did.
No, but I mean, I think it's wrong. But yeah, because I think like before I haven't talked. Somebody who's not shy, or they would like maybe get to personality. In general, like for example, for here, you can maybe say things about my life, like I don't really. Yeah, of course. I mean, somebody who is shy would have maybe like,
We all have that.
So I realize how first impression also change. Like, I mean, I hope mine doesn't change. For sure. I think it's nice because like you realize that you like go to action. They don't judge. I think that's really important.
There was a rumor about it today. Are you working tomorrow? Are you working Saturdays? See, it was a rumor. Who made the rumor? No idea. No.
That's okay. Other guy.
I would say so, yes.
So by the way, all of you installed Rhino 8, right, instead of Rhino 7. So because of the process incompatibility, we need to do one more step. So you need to do these things, these comments. So type the comment and this one. You need to do the following steps.
I think one set doc and then.
I'm fine. I will help you one by one. I will help you one by one.
Set.
And then
Net
framework, yes.
It's like capital.
Yes.
No, runtime. Yeah.
So.
No, right now it's. And they are.
Okay, then you need to write the chart.
So it's net. Okay, I didn't write it right.
Let me help you one by one again. So because this is the additional step that because of the
No, your message is so classy. If I were classy, that would not like those.
I will help you one by one.
No, these are the best.
So you
Like they're so nice. I don't know. Man. Go. Like the end you put it here. Remember, like a window. Let's try to move. I think what is it? No, it's already inside, but not like the thing here.
Because of the language sphere.
Here is shit.
Yeah.
How do we put the window here?
So
Open panel. This is one of commands.
No, no, that's why I take position.
Like that. Yeah. Low. It doesn't let me.
Runtime.
So whenever you go to this one, you will have these options.
Yeah.
Then you change it to that framework. I don't know what happened in his computer that
Yes,
so you can,
But with this.
yeah.
it's just a personal
But I guess we
thing.
have the same problem.
I mean, if you see that I'm using minus 7, this is line 8. So I mean, I'm using max.
Select time execution for the what will be the time like a normal time execution.
Yeah, I was trying to.
No.
Looks like. Select time of
Imagine like, okay, so now then like the floor is yours. No, I will never do that. If I ever do it, like, okay,
Yeah, it's right.
imagine. So it's not that for me. No, but I think you will learn.
But anything, any language is not by.
I think that's because like,
But it's a.
maybe like, because your last thing is like, it's just not what you guys are going to do.
Yeah, because I only have that.
Okay, I don't know what's happening, but let's now actually remember if that's not what you guys
No.
How do we add the algorithm?
Ah,
I think they have the same problem.
Yeah.
No,
open.
but that's what we did. I'm no command. You can make two option plugins every time we restart.
I don't know. No, it's supposed to be just one.
Ah, yeah. I think so.
This is things to be honest. Not well, is there.
Okay, what are some
Non sono numeri iniziali. Alle 15:40 per la roba.
You have tempo. You have so and it says select time.
Yeah, select time.
Okay.
Is that for?
Okay.
Because,
Okay.
cerco la taxa di esame, I can
No, that's not bad.
Did you get your, did you get your second?
Oh, I know.
Did it read?
Ah, the download.
This one. Sometimes it happens.
Yeah.
I think it's fine. That's why probably they meant.
So we'll go to the way Windows.
Do the sex.
But to be honest.
No, thank you. Get more results.
Yeah,
Okay, we'll try it. Maybe help the others. Like, claim it. I don't know. Because we have enough Windows, right?
Yes.
So
So
I went.
maybe.
And I was like, so here, so
Not yet, but I'm trying.
and I was, they have this vacation.
So as soon as possible.
Doesn't make sense. I was texting everybody, like, taking messages a day. Yeah. And I was sending.
Thanks so much. Okay, take the envelope.
Yeah, I'm low.
Should we take
No, 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 yeah, yes.
Right, separating.
Yes, I don't.
I think so.
Yeah.
Different story, different story.
But I'm so. It's fine. So I'm just thinking that it's like dots.
But it's 5 p.m. Are you I don't know, we were speaking about the reservation, and I was like, yeah, we're gonna reserve.
I have to add the.
You can ask, yeah,
But they are not here. So I can instead of.
Okay. Guys, hello. Yeah, I think we can start now. Everyone should have this Rhino and the plugin installed. So what is the purpose of this plugin? So basically, the purpose of this plugin is that we create a more, I would say, this geometry from Rhino. I don't know, something like this. This is just random things, and we can assign the elements, boundary conditions, Neumann derivative boundary conditions, and also create some analysis here, and we generate the data, which will be solved by Kratos. Also, this is we can use this for post-processing stuff. So to test these things, let's go to this. Let's test the post-processing. So if you remember from the previous sections, I already sent you one example, right? The example plus examples. So let's try to visualize that one. So at the end of the day, you will have something like this. This is the simple problem that one that I.
So which file will have to open?
So open file, and then this example single path Kratos .georhino. I will help you one by one.
But all files should show.
I mean, you need also, of course, you need to run it first. This one.
Yes.
But it's not run
It's
like
from this one. Post processing.
okay.
Oh, person.
Examples for the algebra.
Once you see.
I mean, I just want to test whether this works or not. Then after that, we will do the model interventions. I just want to test it.
Yeah, thanks.
Maybe you should open it.
So you need to open it from the plugin. So go to Rhino, yes. Post processing, and then go down. Open file.
Yes.
Where's the file? Yes. Wait, but first, in your case, you need to set the.
No, we already did.
Already did it. Nice. You need to open plug with this plug. Go to the below. I know. Don't worry. They have a similar problem. So where is your option? I will explain to you in a second. I just want to test it. If this works, then we can proceed.
Okay. Okay.
Yeah, it does. This example is in my past, but you need to is it a model? Oops. You need to
Yeah, but the file is not here. That's what I do. The file is available in English as well.
then
What's the file?
we will see the files.
No,
Sample,
I mean,
underscore single,
Very
underscore
maybe
match,
that's
match,
just
just
like.
like.
Where is the file?
The.
No.
Yeah.
So, another folder.
Maybe the future we can find it.
Yeah, once I got a folder.
Go to the right,
Okay,
I
now,
eight.
Gas.
I think everyone will be on the same side, then we can start.
And in sample, single match.
Okay, right, now we can start. Right. Now, maybe every one of you is wondering what is Crocodilo, what is why doing it that. So first, I would like to introduce you to this GitHub page, Crocodilo cat slash Crocodilo. As you can see here from the explanations, this is the pre and post processor for the geometric analysis with Rhino and Grasshopper. So I would like to, I would say about this name, Tobias Dasamacher. He's the one who started this project. I mean, this Crocodilo GitHub page. I also involved with this development. And yeah, basically, the idea of Crocodilo is that so we have Rhino as the CAD software where we have, I would say, we are able to create the CAD models, doing the eyebrow and so on. Then we generate that. I would say the input files on top of that and use Kratos as software, then refer it back to Rhino as a post processing. So basically, this is I would like to say Rhino is not free. I mean, what you have right now is the trial versions for 90 days, I think. But this one, this plugin is also an open source. So in the case that well, the purpose that why we have this session is that maybe in the future you can generate. I mean, I will show it to you in a second how to generate the model. Sorry, the Kratos input from this using this tool. That might be you need that. Well, I don't know for the purpose of your project, but at the end of the day, again, well, the most important things are the input files. Once you have the input files, you can do the modifications by yourself, either with Python script or doing it internally in Kratos. But these tools is specifically just to get this geometry, get physics, blah, blah, blah. Right, let's do something more interesting. All right, I need this.
Listen to a little bit because it's very good.
Wait a second. Let's do one more thing before. All right. So we have the first example. I will also do the same thing, but now I will make it more interesting. We have two patches. So we do coupling here, interpatch coupling. I will do the same thing with Rhino. We have this the derived boundary conditions. We fix this side. And this side we have again the Neumann boundary conditions. Let's do it together. I don't know. Let's make it E equals to 3, Q equals to 3. This patch E equals 2, Q equals 2. They have a similar length. And yeah, let's do it together. first, you need to create the paths. So this guy, this surface. So you see here, first corner of surface, let's make it 0, 0.
Centimeters file.
So you open a new file in Rhino, it has 1 centimeter, meters.
No, it doesn't.
So this is the one we need for post processing, we close it.
Yes, you can go there. We start a new one. We will start a new one. I would like to create those example,
We can save it wherever we want.
or you can
Yeah,
do
yeah,
it
yeah,
again later. So let's make it first corner 0, 0, second corner 5, 0, third corner 5, fourth corner, yeah, you know, I'm creating a square like this.
Single line really.
It's not a single line, this one. Surface from 3 or 4 corners.
So here you remove the.
So here you click that guy. If you click that guy, you can see that command first corner. Just type 0, 0. I mean, I'm creating.
Zero point.
I will help you.
0,0 and then 0 of the surface. Is reactive. No, okay. I mean, I'm 0,5.
In square people, I would say like 5.
Yeah, and then so from the top,
5,5.
like, you have to keep all the points. Or yeah.
Yeah.
Yeah, and then zero. 5, yeah, 0, 5.
Yeah, if you want to first.
Yeah.
Yeah, what's the top? What top?
This one.
This one.
Yeah.
So something.
No, it should be something.
It depends on the display.
One of these is.
You can create it manually, but if you create it manually, you can see.
Not exactly.
Exactly, that's why I'm using it all images.
Okay.
Exactly. I mean, you can change it, but well, you can do it. But anyway. Okay, everyone has a square? Yes. Now, we do the same thing, we create the second square. From 5,0 to 10,5.
No, 10,5.
Yes, you can see it.
Like this, so you have two squares.
The length,
No.
like how
No.
it's 5, 5.
Well, it's up to you. I mean, 5, yeah, I mean, the fact is that you can just create another. Like this. So pick one and
I think. Nice. Yeah. Yeah. No. How can we put the grid? The grid on the background. It's too close, maybe, no?
the thing is that I don't know exactly maybe it's because of the
It's millimeters.
millimeters.
Is that bad? The same.
Well, it will be 10.
Okay.
No,
Okay.
because we have diamond, we are diamonds, like that.
What did you choose? Like the dimension.
Meter, if I know this thing. I mean, but this does that. At the end of the day, you will generate that number.
Ah, that's cute. I thought it was in the L.
I mean, I'm here not teaching you how to use Rhino, I'm here to teach you how to I mean, there are plenty of courses how to use Rhino, but we don't have time. So just follow it. Okay, everyone has two squares?
Yeah.
Nice. Now let's do this. We will do, I mean, we can like these points on and select the objects. Then you can see the control points. Points on, and then select the objects, and you will see the control points.
How can,
And then enter.
how can we delete?
Yeah, you can. I mean, you can see the points here. Those are the control points. And well, I would like to do the P refinement here for the first parts. For example, P equals to 3, and the second parts P equals to 2. And how to do that? We use the command change degree. We do it one by one. So we do change degree. We select the first square, and then you see by default it has degree 1. We change it to 3.
Where do you see the degree?
Change degree.
Yeah, but where are you seeing the?
Where you specify the B there. This one.
This is like and then just this and now you're going to see the
That's
But we have to type 3.
yes.
Three from the 3.
No, because we
No, 3 from the 3.
No, no, because
nice.
so let's three ones.
Oh,
Yes.
And you multiply
but why do you
change? Change.
Select one.
Select the
object.
select the first object, right? What is the first one? Yeah, we should wait.
Click this.
Enter. Now it asks you the degree you want. Because it's U and V.
And then the same thing for the second part, but V equals all right, now we are doing the same thing for the second part, but using degree.
Okay, now choose.
You will have something like this.
No, I think it's the same.
So basically, this is how to do P refinement. And now the next step, we do the not insertions. Let's do it on the second part. Let's insert one element here. So what we need to do, this is the command insert not. Then then we select the surface, in this case, the second surface, and you will see something like this. Just stop, we will do it together.
Sorry, Ricky, these commands change degree and insert not are from Rhino or from Cocodrilo?
From Rhino, all of them. Now I'm waiting for everyone to be at the same step because this is very important, and if you miss it, it will be hard. proceeding to the word. So I will wait till this step. I mean, just wait till that step. We will do it. Right, from here you can see comments, automatic, midpoints, symmetrical, directions to go. What I want to say, the most important thing is these directions. So, well, it has, I would say, three different options: U directions, V directions, or both. We can click directions, and you can see three different options: U, V, and both. Well, in this case, to make it easier, we do both. And then we click automatic. As you can see now, we are done. Not insert yet. After that, and back. That's it. Now we are almost ready. Yeah. Automatic. Yeah. And yes, yes. And so when you are stop. And the next step is that in this case we have two different patches, but what we want to do is that we want to have them as one patch. So we need another command, this one, this button. This button it has the purpose to join two different patches. So you can click on this button, join, and you can select those two.
Join or join copy?
Join. Join this one, and then you select both patches.
No, just select the
Patches and done. Now they are in one entity.
Most of the control points.
Unfortunately, after you join the patches, you can't. But sorry. No, not yet. You are not able to do that. I mean, we can try. So points on. No, you can't. If you want to see the control points, just do the other. We need to go explode these things and.
What are you doing now?
Explode. And I just yeah, from the join pass I do explode and revert back the into, I mean, that couple cuts into two different cuts. But well, I mean, what we need right now is to couple and those two patches. All right. Now let's make it bigger. Just I mean, just double click here, top double click. Maybe make it bigger because this is important. Now we need to assign the elements, the boundary condition, and so on. Now we do the thing. Okay, first of all, please let me know if I'm too fast. Now let's go to the element. Properties element shell.
Where?
This one. So if you see properties, we have element, refine, blah blah blah. Let's go to the element and let's go to shell. Then, yeah, I think we can keep the default value, thickness equals to 1, it doesn't matter. And if you click here, if you scroll these things, we have a lot of options, but we will go with the default one, shell 3P, the couple of shells. And then for the material, we use the default one as well. Otherwise, we can modify the material here, but well, I don't think we need time. We have time to do that, but well, we can use the default material. And for the coupling, to make it easy, we use coupling penalty condition. We can also change it into Lagrange or meter, but at least for these examples, we will keep the default value. So thickness 1, shell 3P, still coupling penalty conditions. Okay, and then add element, click add element, then you can see select surfaces, you select this guy. Enter. Both of them, yes. And then enter. If you scroll down a little bit the plugin, you can say, you can see here options show elements. If you see the, let's say the different colors, it means that you already assigned the elements. Sorry, because this is projected, but it's not. Yeah, you can see the blue color instead of black. Oh, yeah.
Sure, it's changing.
But I can see, yeah, but it's changing.
It's changing. Yeah, I'm blind. Ah, yeah.
Now.
Yeah, now we have. Yes. Yes. Yeah, because of that. Anyway, I can see that it's done. I remember my copy comments.
Okay. We added
I didn't see
We need to see the inputs. Right now, just follow me to assign all the element conditions that we need. All right, guys.
Really, does matter if I have assigned the element 2 times?
Doesn't matter. It will. I mean, the newest one is the element. I mean, for example, you change the thickness to 0.5, just replace it. Okay, anyway, now we will assign these support, the required boundary conditions. So you go to properties support. And in this case, I would like to assign to the surface. So click surface, structural element, surface, and line, surface line. And then, okay, here we go. So here, I would like to have just a simple, I would say, load in the X direction. So we don't need the rotations support. We just need displacement X, displacement Y, displacement Z. And then after that, you can just click add support and you select this line. Click enter. And then again, you can see show support. Yeah, and in below you see options show support. If this works, you can see something like this. I will show it to you after we get it. This is not on because it's not on itself. So we coupling with melody. So we coupling process of Alright, now we assign the Neumann boundary conditions. Do the following the same thing, surface line, but in this case I would like to assign in load at the x directions. So put 1.0 x. The rest are zeros. Yeah, 1.0. And then I add load to this line. Something is right. See that?
Yes. Wait, no, you have- Sí, lo menos.
Now we can scroll down and in this case I think we can go to the start I would say simple linear structural analysis. Well, we put the name, for example, example something like this. Scroll down.
Yeah.
Analysis, linear structural analysis, just write the name, I don't know, example 2 or something.
Create analysis.
Then create analysis. Then you should find your example 2 here. We will stop at I will stop at this point, so I will wait.
Not example 2.
Example 2, create analysis, and then here you can see the example 2. If you I would say
Can you do it? I don't know why it says
yes, then
Rerun.
Then okay, then we run analysis, and please go to the folder where you store the plugin. So in my case, so it supposed to be here. I can see example 2. I have plenty of examples because of my work, but anyway, you will see something like this in the folder. Example 2, you see. So yeah, those are, I would say, the inputs for Kratos, the geometry.cat, this Python script, Kratos Python script, materials, physics, parameters, refinements. I will tell you about this later. But let's check it.
yes.
If you need more time, you can make it mine.
Okay.
No worry.
So long
I think it is more important what you're planning than what I am actually.
okay. Thanks. Now, before we check the file, you can try to run it with Kratos. So yeah, as you know, the CMD and file version and run.
Okay, validate you PWD, which is
Okay, go ahead and watch yourself.
the left doesn't exist now. How do you show the these like privacy of the test? Where are we? Okay, download.
Sorry guys, there is a small bug. I will help you one by one. There is a small bug reporting parameters. Yes, okay. I will come to you guys one by one. There is a simple bug, small bug. Sorry.
Saying that the dependency action coefficient.
Yes. Yeah. There is a small bug. I will fix one by. By the way, do you have Visual Studio? No.
But I'm running it.
No,
I
I mean this one. This one.
But I'm running it from the.
Because here, as you can see, this is a JSON file, so we have it in one line. This is nested. We use there's open page. You can open it with Visual Studio. Modify the JSON. There is a simple one. I'm sorry. Yeah, it's an operations of code.
Why is it?
So bright. Anyway, we can use Visual Studio to recognize.
That's the lowest. Oh.
So, okay, let me so what I do here, so this is the one. Visual Studio. If you click this,
Sure, we can copy paste it.
Just
I mean, it's quite old.
The problem is that we don't know.
Yeah, but
Yeah, exactly.
I thought we still have.
I put these extra output which is still in the process. I mean, still in the opinion. So we need to remove this one process.
Sure. Yeah, and like, yeah, turn on down.
Can we copy
Yeah, I want to meet like super bright. I don't know, but I mean, that's a personal.
So there's a small one with where is the can you open this in Visual Studio? Not Visual Studio, no, Visual Studio.
It's just random things.
Sorry, one printed. I have to get
Just believe me, I'll be able to like convert it to the fonts.
Is that if you open Visual Studio Code, we still have one more.
The games code. And I just write them and go through that.
No, and you also have to delete this.
Yeah.
Also, what was parentheses?
One is the Visual Studio is the you go here, we can type it now. Yeah, and the front.
Which one? Enter the. All the things that. It's 90 minutes.
This is what related to extra process which is not needed for this one. This is inside the process possible. So sorry.
Just delete it.
Yeah, just delete it.
At the end of the parameters.
Ah, there.
Try again. Save and run.
Run. Yo, no, no, yo.
Now you should have a folder, you don't imply, that you be able to read in RAM, I don't know.
Yes.
So it's not meaning
The six that you have, all those post process, those are the.
Okay, perfect.
Now we have, yeah, yeah. Yeah.
Not that much.
Now, let's go back to Cocodrilo, sorry, to Rhino. And we will check, we will do post processing stuff. So post processing.
Where?
Post processing. Yes, yes, go to the other tab. So post processing and try to check the results.
Open file. Which file do we have to open?
The geo.
All of them.
I mean, so open file, this one.
Ah.
Geo. So if this works, you will see the result.
Sweet.
Did you have to press anything to show?
Click, yeah, sure.
Ah.
How you say?
Okay, we will back to your. I can work with you in person.
Yeah, I think one guy gave me a memory allocation problem.
I mean, I can smell this.
Okay. But you can have everything, right? You can run, you can see it also.
Is that the
Yes, just a focus, you just want to check whether
But
you.
why is it so interesting?
It works for the others.
It says problem of relocation.
Well, so the others like first because it works for me. Okay, let's
Because I thought I moved the cursor.
Okay, let's.
Yeah, maybe with the. This is like a cursor to see the different lot of. There was like a cursor. There was like a cursor.
But now. I think it's visited by anyone.
Okay. Let it be stolen.
So I'm the Swedish one, so what,
If you want to print the post processing.
is processing?
Yeah, there is this, yeah, on top of it, there is a cursor, this cursor, yeah. This is the load step, right?
Yes, because we are,
We try to go from 0 to 1,
yes.
that's it. Yeah.
I mean,
It's just and then it cuts.
we have a linear, I would say, linear analysis problem, so it should be only one workpiece.
Yeah, I just haven't tried to do from
I
0
have
to 1.
also like another application that
I don't
like
know
an emergency save. There appeared the new application that is called the Rhino emergency save.
Rhino emergency.
Oh, can I check your input?
Yeah.
What does it say? What does it say?
It's impossible to complete the operation because the other program is occupied.
Okay, so let's check your input. Maybe something's wrong in the input. That's
Okay.
fine. Maybe.
Okay, it's open.
No, please check the input first. I'm assuming that we will get the same message.
Maybe, yeah. Yeah, right.
No, I mean,
It's so, it was so.
No, it's not the problem.
yeah, it's solved the problem, but yes.
So you're missing people. Oh, that's great. Yeah, but doesn't matter. Like they're see how it works. And then someone outside
this.
I think there's some people.
I'll give it some time.
No.
This
This
is
is,
exactly what.
this means that sometimes when we are doing simulations, this, I mean, you see.
So you think something is wrong?
Starting from we play book now. Exactly. We just open it.
Yeah, you have no date. Well, I don't know what you're going to do every
Yeah,
I've never seen it.
all of this.
From the, like, years later, it gets super nice. Yeah.
Like, I have some. There's a lot, like, there's some stuff, like, this narrative. We have their program.
One also has the same like problem as experience, but the other they are fine. I'm also fine.
One didn't work. He has a secret.
You have to go to
Because I can probably. That's my fault.
Let's
No. I have it first.
Yeah, we can trade for you.
To be honest, there's no. There's no.
Yes, the problem.
Why?
Okay, now the questions. This isn't doing. No, this is mechanics. This is mechanics. So by accident, if you remember, I assigned the load maybe you forget to include the Z. And I want to assign it. Okay,
Yeah.
you get it. You know?
So it's just the force in it.
Exactly, because I wanted to assign for the support, I don't assign the one. Yeah, that's why you can see.
So what did you do?
I left and then already.
Problem solving. Okay, so that's all because I solved it.
I say like they go down to this nothing kind of.
Can I check the second box again with this one?
Yeah.
At least that you lose. You know what I
Because might be you have to see the cover like Andrea. So projection. Just like
Between the two.
Okay.
No, I
The one that you.
you can just like about
because they have.
Is version the first?
with one
Okay,
edge.
sorry.
Is
That's
version
fine.
the first? Is the first?
But I'm
Does it different when you use the cursor from
You have the temp now.
One,
Yes.
you want
You know?
to crash, yeah.
You know,
does it
I think one. Okay. It's a problem under
and then what problem? But I think by default when you press to add load, because the load on this direction is you have to remove. So we basically type
It was
Yeah,
the.
but I
X
want
and
to
the
apply
load.
the displacement support. I don't.
We had
I-
to do the default.
No, the thing is that you can apply the rotation support, but in this example, I try to make it as simple as possible. So only to sign the displacement support.
Yeah, but you were saying that.
Yeah.
But I don't was
But
the
it's
one
not
direction.
so of course on that,
Yes.
but then we have to so it was like moving
The cursor and then you can go.
No,
I would propose to make a short break now, so that we can say bye to Roland, who's leaving. And then we can resume with the same. So I'm willing to give up completely the next slide.
No, I think we will be done in 20 minutes.
So anyway, let's go. Let's take a break, because Roland asked at least to say.
Okay.
But then you resume, okay? You resume.
Sorry. Yours will be the initial one. There is a bug.
No problem. This is not that. This is our one.
Nice days, as we have been so many. Well, I still did not really recover from yesterday evening. I don't know. Okay, I really learned too much, and I'm not used to it anymore. I hope that I hope that they did not appreciate. You're in charge of putting the pictures to the folder. No, we have.
They hydrate.
Yeah, I have too.
They hydrate. No, I know.
I
Hydrate.
alongside.
Okay, cool. No, is that your vibe?
It's very live.
If it's your vibe.
No, we're talking about like, let me do this. Oh, like, I aspire to be a light traveler, but it never works.
You have a bag of 25 kilos. 23.
But, I mean, I didn't feel it to the max, but. I do, but I don't think that's the.
Yeah.
Right. Really like that.
Actually, that's not how I say it. I don't think anyone.
Yeah.
I just one hand.
More than
I agree to it. I use only one hand.
Ah, but how? But why do you think this is true?
Yeah, non regular. Yeah, how do you like to make the division, say?
Okay. Now let's finish the skills. Right, you can play around with the tools, but to be honest, we still have a lot of bugs in these tools. For example, this is to show the ghost points. We can also do some type of scaling here, for example, 100 and show. Oops, not work. Sorry, not this one, but this one. This outscale one. Oops, what's wrong? Sorry. Yeah, let's anyway, this is not important. So, well, you can do, for example, here to show those points. And for example, you can.
You just scaled it up.
Yeah, just no, this is not working. So it's, I will check it. But anyway, you can just, for example, here to show the ghost point.
How did you make those points appear?
Ghost points.
Ah.
Okay, I have a question.
Yes.
In the beginning, it was three points on the left and then two, and we defined two. And on the right, it was like 1/3, 1/3, 1/3. And
Sorry,
no, on the left,
I get your point. Wait a second.
and then it was
Sorry.
half, and the other.
Yeah, I opened the wrong file. Sorry, I opened the wrong file.
No, don't worry. Just, I want to ask something from the previous for the refinement.
Yes.
Why do you have more Gauss points and tangents?
I will come to your place.
Yeah, first.
You know.
No, I don't know.
I don't have problem.
This also.
I don't want to miss that.
Something here, let's say you are integrating the boundary. Actually, the functions, let's say you transfer the snakes.
Yeah.
Which one?
Because we it is the and I only apply this based on boundary conditions, so it's like
Yeah.
But we treat those
yes,
Something like-
I don't know
penalty.
when you
See,
It's like
the alpha.
I think
last
you have to force
Yeah,
it
alpha.
to be-
There is exactly. Human.
we have to reset when.
let's say I'm gonna get into one.
No.
Yeah.
Human capital.
Are we to start again or no? Ah, that was the one who created it. Yeah, first. Yeah.
Oh, yeah.
Thank you.
No worries. Now, let me just show it to you the input files. So please open all of the input geometry, materials, physics, for the parameters to the Visual Studio. And let's discuss about the input.
Sorry, really, what you have to add?
I mean, let's open the input file. I would like to show the no, the Visual Studio, because you need, I mean, yeah, you know the problem, right? It's on time, we need to expand it.
Actually, I was going to see that because we provided it.
I would like to discuss the input file because now we have the coupling. What is the difference between the input of the couple problem with the simulation with the single facts? That's what I want to show. Yes.
Yeah.
Yes. All the inputs. Yeah, you can expand it. Nice. So good. Right. So that's right. Okay. All right. Just a quick questions. What do you think about these phases? How many phases should we have in this example? So in this case, you see that we have one phase with BRFID2. I don't know, maybe this guy, and the other one with BRFID2. If you go down, you can check it. So this is, I would say, phase 2. Let's say like that, and this is phase 3. And for each phases, it has still again 4 training curves for an obvious reason, right? Because we are not play, I mean, we are not dealing with trimming yet, so it's still like this one for each phases. But be careful about the edges, because here, I mean, so if you go to the edges, you will see that we only have, in this case, wait a second, 1, 2, 3, 4, 5, 6, 7 edges.
I will send you all your contact, so. I think he's waiting there because, yeah.
Okay, now, why we only have 7 edges instead of 8? Because there is one special 8, this 8, 7, who is the coupling 8. So this guy. So I can imagine that in physical space we have 1, 2, 3, 4, 5, 6, 7 edges. This
Which language? Sorry, not see.
what? It's
448.
400.
448.
And this one is the coupling edge, I would say. And if you see the topology, these coupling aids refer to phase ID2 and face ID3. So I mean, this is how we deal with the I would say the coupling example. That's why we only have 7 ends. Just want to show you all this. Then so if you go to physics, of course, phase 2 and phase 3, they are the shell element. This is the H6. Am I right? Yes. Where I applied the support penalty condition. And if you scroll down, you see, you remember the H7, the coupling H. Here I apply the coupling penalty conditions. And last but not least, there is also this one. I apply the Neumann boundary conditions. For the materials, since we have support penalty conditions and coupling penalty conditions, I need to assign 2 penalty factor, one for the support and one for the penalty. Of course, the number you can change it manually, or if you have predefined penalty parameters from which you can create it on the Python script, you can change this value. Last but not least, here in project parameters, you can see that, for example, here, let's go to line 104. The, I would say the delivered process list, we assign displacement 0, 0, 0. We also assign the coupling. Yes. So first one, I assign this guy, the displacement, and we assign the coupling. And now, what I want to say is that since by default we assign displacement and coupling, both of them, with a certain, I would say, manipulations, we can remove this one, but it's too advanced to be discussed. And yeah, I think that's about the input files. Do you have questions so far?
So in the beginning, there was a 30-degree approach on the left mouse, and the second.
Second, you can check it.
Yeah. But then we defined the.
No, at the beginning, by default, P and Q equals to 1 by default. If you create a square in right by default. By default, they will create just a simple.
Okay, and then we made it.
Then we do P refinement here, and here we do K refinement.
So let's say in Rhino you have the simplest representation we can mode of the geometry.
Exactly, yes.
Okay, and then we made the.
For this one, we do P refinement. We increase the polynomial from 1 to 3.
Okay.
This one, we do K refinement. We increase the polynomial to 2, and then we insert the nodes. K refinement, remember? P refinement first, then X refinement.
So in the first, there were like 4 nodes, they split the one side to 1/3, 1/3, 1/3. And in the second, there was one.
Yes.
3 counterpoint, so
yes.
0.5, 0.5. And when we did refinement, it went 0.25, 0.5, 0.25.
Yeah, something like that. Yes.
But this doesn't coexist because it was 0.3, 0.3, 0.3. It was 0.25, 0.5, 0.25.
Yes, exactly.
And then how does it?
Then you need to refer to my presentations on Wednesday about the projection. That's how we do the, I would say, the advanced coupling. So we do the project from the slate because this is non-conforming cases. I mean, we need to, I would say, map this from the slate to master.
This is what we.
Yes, exactly.
Okay.
So
now the refinement, G refinement.
I mean, we.
There is the
There is the file refinement JSON.
I forget to. So this one. Yes.
Okay, here we don't have to increase degree. I mean, here we see 0 and increase degree U and V for all the values.
Of course, you can do that. Yeah. Yeah.
But I mean, if we put 1, 2, or whatever, we
You
are
will
increasing
do
the degree.
refinement on this geometry.
Yeah. Okay. So starting from 3.
from 3 and 2.
So it's like the 0 that Nicolo was referring to, no?
Yes.
Which in this case was linear. He started, so to say, from the 2 initial
Exactly.
values that we started.
Exactly. But for me,
Right.
just to make it easy, just to demonstrate the things here, I do the refinement in a way. Of course, you can do the refinement within this script. It doesn't matter. It depends on.
And then you, with this script, you, as we did before, we just run it and get right with Kratos. Thank you.
Well, to conclude my part, I think I just want to have one small comment. So what you did so far is that you have the plugin, right? You do it, you import the plugin tool options and just import it. I mean, I give you the plugin, like the executable plugin. But what I want to say is that we have this branch called Cocodrillo. You can, I would say, clone this repository, and inside this repository, you can see that this is how we kind of write the input from Rhino. So I can show it to you, for example, here. I will post my Rhino. Sure. Oh. Close it. What I have to show to you. Let me open my Visual Studio. We So it's, I mean, if you, I would say by any chance, how to say that, compile this repository, you can do something like this, where you can debug yourself here. So for example, I open my model here, I open it via Visual Studio, and for example, here is my repository. If I put something here, of this official, for example, I put say breakpoint here, and I assign this element to this. So it will go back to the code. So you can do easily. I mean, you can debug this plugin if you need to add something, remove something, and so on. I just want to let you know, maybe some of you will work with this plugin, and this is easier to debug if you compare to others.
Can you repeat it? How we debug it?
How we debug it? So the thing is that, oops, sorry. If you go to this repository and you clone it, then you will find sorry, this is oops, one more. You will find yes, this one, cocodrillo.slm. You can, if you click that, if you have this Visual Studio Code, you open this in the Visual Studio Code, you have this cocodrillo. Start, and you can do debugging via Visual Studio Code. Sorry, via Visual Studio, not Visual Studio. And then you can just put certain breakpoints in the CS file. This is written in C#, by the way.
Ricky, and for very large CAD models, is Cocodrillo robust enough?
No. The thing is that
For example, you have to model a complete wind turbine.
Exactly. What you need to do is that you have this, I would say, rough CAD model, right? You have a very rough CAD model, and what you need to do is that you need to clean it to make it, I would say, to be readable in Rhino. So, wait a second, I have the answer of your question. If you remember the presentation of Roland, the very last slide, this is basically the model that you will get from, I don't know, from the industrial guy, right? This is very rough model. You cannot, using this, no go in Cocodrillo. This is what you get from the designer, right? And then, well, as an engineer or you need to do, I would say, I would say, doing like kind of trimming and cutting, creating of patches, and this is like what we expect as an engineer expert. This is what I mean by cleaning model. At this step, you can use Cocodrillo and Rhino. Cocodrillo and Rhino. That's it.
But let's say practically, what you have to do to obtain that geometry.
What do we need to do to obtain geometry?
Let's say I get this geometry from a designer. Which
Yeah,
step,
yes,
which step
exactly.
you have to accomplish to be able to use Cocodrillo?
Well, you need to make sure that, for example, here you have multiple patches, you have trimming. You need to make sure that if you remember the water pipe and some other, I would say, lost connections, you need to make sure that it won't be there in your in the model. It needs to be connected. So when you click
So
join,
you have to zoom your seed.
yeah, exactly. Well, that's the truth that, but that's, I would say, still open question, I would say, but
It's not automatic.
There
let's
is
say.
something conventional. This is what they work on. This lecture. This is what they do. They make it easy for you. Like you don't go node by node.
Because otherwise you have to zoom in and start looking for the defects, let's say.
Yeah, this is why nothing works like this. This is like completely this is like conventional.
exactly.
But
So
basically-
that's why we are here. We need to improve. This is the limitations that we have right now. If you're asking for the practical applications, this is the limit. You need to do this right now at this moment.
So that's the bottleneck.
That's the bottleneck. So then we are here. We need to improve this stuff. I don't know, maybe you can have some, instead of I would say, the coupling, I would say forcing the couple, you can do something like make a tolerance, for example, the water tolerance, and then improving, I don't know, embed it or whatsoever. So to answer your questions, that's the limit. Otherwise, we are not
And it's
here.
like next generation. It used to be a really cumbersome process. Now, for example, in NASA, you hit a button, and there are so many algorithms to derive the optimalness, and you just make it go and inspect. But it's fully automated. So 40 years ago, it used to be like a guy going.
So what I want to say is that again, at this moment, unfortunately, we need to do something like this. We need to do trimming, we need to do the couple more manually, and at this point you can use whatever auto that we have, generating the input files from Python, then solve it with Kratos, with the multi-pattern technology, then do the post processing. But from that point to this point, oops, sorry. Yeah, it's still
Okay, suppose you have a perfectly watertight model, then you could be able to process it
with Cocodrillo, yes.
but it needs to be watertight.
At this moment, I would say. But me and Tobias, we have tried, I would say, to make it some kind of tolerance. So it's not fully watertight. We can put some tolerance and we can still do the coupling using kind of embedded method. But this is too advanced. I don't have time to discuss that here. We do it a very different way, like what we have done in the last 2 hours. We do it in an embedded way. So we embedded coupling. So we can have we can couple this guy if the tolerance is small enough than a certain number. or we can, yeah,
But that's not normal library, it's embedded library.
yes, it's embedded algebra. I don't have time to talk about that. I'm sorry, but that's how we have tried. And with this embedded algebra concept, imagine in this example, you couple two patches. How if I want to couple, for example, more than two patches? For example, you can imagine this is two patches, right? We couple it on this line. Okay, in these things, I want to couple something like that. At this moment, this is not possible using the things that I discussed before, but with the one that I taught, with the embedded algebra, which, well, I think I will talk about that. I don't know, not now. It's doable to couple something like this, or even multi,
More than two.
more than two, exactly. Still a long way to go, but yeah, we are aware about these limitations, and yeah, again, that's why we are here. We are trying to these problems. So more questions before I finish my part.
Maybe doing an example with some trimming curve.
No, it will take a lot. I will do it personally with you, and if someone needs that, they can contact me.
You can ask in the project of parameterization,
Yes.
The part regarding the coupling, I mean the dirichlet processing is
Yes. Oops. Okay. I will try to-
yeah.
This is the default input for this Python module.
Even if you can skip
Is
that.
that
Yeah, it's the but you cannot see
So if there is no more questions, I can pass it to Nico because I think he has something to present. A couple of slides about his results. So Nico, please.
Before we have played a bit with the Laplacian element that's there. Yeah. Here, let's retake the same folder as before. So the Kratos EGA develop. No, sorry, this one. Okay. And then I will just show you what I add to this example for implementing the SPM. Okay, so I introduce an internal trimming curve in order to represent an internal object. Like this. So it's the same problem as before, but now we have still the same problem. Okay. We have that u is equal to ud, so some Dirichlet boundary condition on gamma 1, let's say. This is on omega. Okay, this is gamma 1. This is the external boundary. And then we have an object. This is gamma 2. So also here we have some u is equal to, maybe let's call ud1 and ud2. Okay. And we impose this internal boundary condition with the SBM, but we could do it also with standard data. For example, in my in the presentation I showed you 1 month ago, something like that. At the end, there was this picture that might be useful. Okay, this is a classical timing. You see, we are this. I did this with on a Rhino. Okay, so on a Rhino, I create the external boundary and this internal boundary. Okay, and this is my domain. The blue dots are the integration points. Okay, and you see that on the Catalan knot span, what Ricky do if I do a zoom. This is one knot span. Okay, let's take this on the angle. We have here a timing curve. Okay, this is the zoom of this knot span here. Okay, what Ricky do? Then correct me if it's wrong. He create maybe a triangle, do a triangulation. Do you 4 triangles or a lot of triangles? Do you build like only 4 triangles or more?
4, yeah.
4. I don't know how.
Just do it randomly. That's
Yeah, let's do randomly. Okay, he creates some triangles. Okay, and then on each triangles he take some Gauss point. Okay, to integrate also this part. So he will, and each of these will be again one Laplacian exactly as before. Okay, Laplacian element. And in fact, you see here a lot of Gauss point. Instead, what I'm working on is the SVM, and maybe here you don't see very well, but if we do the same with SVM, we take the same knot span. Here I still have the same, but we call this the true boundary.
You make it bigger because.
Yeah, bigger than this. Yeah.
Don't you want to draw it on the blackboard? On that?
Yeah, I think it's better.
Do you want?
you can go with these.
Yeah,
It is there, it's open.
Yeah.
Ah, you can. Yeah,
It's some of these.
yeah.
Now,
Add.
Yeah.
make it large, full screen.
Yeah. Let's take cut elements. Okay. Suppose I have like any true boundary. This is my true boundary. Okay. The SVM. Okay. The trimming techniques just build some triangles and find some Gauss point. Cannot go back here. Here. Instead, the SVM finds a surrogate boundary that in this case might be this one, for example. Okay. This is my surrogate boundary. And we will impose some modified condition on this boundary. Okay. In this way, we don't have to create a Gauss point here. In fact, if you go back on my presentation.
So you modify the boundary condition to take into account that you're using a different boundary.
Exactly, because here I'm not taking like any Gauss point. You see, I don't have any Gauss point in this cut element.
You just have complete elements.
Exactly, I have just complete elements. So I avoid completely to cut and create a lot of Gauss point in the cut element. And then it's different. It's as you have seen with the presentation of Ricky and also the ones of a manual. It's very complicated to integrate the CAD elements, especially then do 2D, but also in 3D, it's even more complex. So with SVM, it's easy, okay? But of course, if you want to preserve the same P+1 convergence, you have to impose correctly the boundary condition, and it is possible to preserve the same P+1 convergence also in this case. So without integrating those, but of course you will not have the results on these CAD elements, because there we don't have the Gauss point, and also the basis function. They don't. We have not a basis function there.
Once you get the results in the quadratic points inside the elements, you can extrapolate.
You could extrapolate, but yeah, you could extrapolate, but you don't have all the coefficient you need, because you might have here some basis function that are completely deactivated. Okay, so yeah, you can extrapolate, but it's not straightforward. We haven't done it yet. Okay. So if we go back to our example before, and then I show you the differences. So you have on your computer, all of you, maybe feel it was not working for you, the Kratos, but so this is without the SVM. Let's do one last example, just so that if you have any question, okay. Let's go on the project parameter. On the project parameter of, remember this was as before, the one we have used before. Do you remember? Yeah. So open again with Visual Studio, and impose a third order solution. Maybe before I explain me too fast, but what I did is, suppose I take as the exact solution, let's say this function, x to the third power plus y to the third power, okay? And then f is known. So I derive f knowing the exact solution, okay? So I put u in this equation and I get f.
So it's an engineering solution.
Yeah, it's a manufactured solution, okay? In this way, it's easy to compute the L2 norm of the error at the end. So this is the derivative of u, the x squared, plus second derivative of u, the y squared. In this case, we get 3x squared, 6x plus 6y. Right. Actually, here there is a minus again. I forgot always for the minus. So here we have a minus.
You have to manufacture this solution.
Yeah. Okay. So in the project parameter, we have to modify the value we want to impose weekly as before on the Dirichlet, and also the f. The f is it flux. So I make it bigger. Oh, okay. So the heat flux is not minus 4 anymore. It is minus 6x minus 6y. Are you at this point, everybody? Okay. Now remember, we have to also the convergence on the convergence script. We have to change the exact solution, because we are changing as exact solution this function.
Sorry, Nicola, you changed the flux and what else? Which other line?
Line 86 and the value of the boundary condition, line 69.
So
okay, I have commented one, and now we are using this as the solution of our problem. Okay, and in the convergence main Kratos, where I do the convergence study, let's use this exact solution. So this is just to do the post process at the end. So we give to Kratos the boundary condition, the forcing F, and we solve. So we have the solution inside the domain, and then at the end we check if the solution that Kratos gave to us is equal to the analytical solution to the manufacturer. So all at this point, refinement. Don't forget the refinement. We have to choose the degree of freedom of the basis function u and v. For example, let's use quadratic, so 1 and 1, because 0 is linear, 1 is quadratic in my case. Okay, so 1 and 1, and then we can run the convergence study. Let's see if I made some mistake. Now we are simulating 5 cases, doing H refinement. So as with insertion 1, insertion 3, 7, 15, and 31. Okay, and we see the convergence study. So we were using quadratic basis function, and we get third order velocity 3. Okay. Did you get the same? Very good. Just let's use third order basis function. What do we expect? Yeah, but since the solution is third order, we expect to obtain the analytical solution immediately. Okay. And we get exactly. With the method is increasing, but it's 10 to the minus 30. So we are getting the analytical solution. Okay, since we're using third order basis function, and our solution was a third order polynomial. Okay.
You can check that you're using third order basis functions in
The refinement.json. Refinement.ega.d.
Which one again?
Here in the refinement.ega.json, we set the degrees of freedom, the polynomial order of our basis function u and v. You see, increase degree 1 in u. Okay.
Did you do something else apart from that?
No. What did you get?
A little bit extreme.
But never.
No.
Okay, maybe what is low? No, the last one.
Yeah, the last one is
I don't think it's funny. You see, the first 4 iterations getting so
that's why we get
okay. Okay, now you don't have this example. I'm moving to my second Kratos. I have 2 Kratos in my computer, one with the SPM, the other without the SPM, because now presentation still. Okay, so you cannot run at this part. I can only run this part. Let's see. Okay, I'm using the same problem, but I have also this internal boundary now. Let's see the physics. My physics dot ega dot JSON. See, I'm still using my Laplacian ij element as before. Okay, this is the same as before. It's this domain. Then this is exactly as before. I'm using support penalty Laplacian condition, the one we have created together before. Yes, with the same with these BF IDs are this one, this one, this one, and this one. Okay, it's on gamma 1. I have penalty condition, and the next block, so I add this block to the project parameter that is the SVM Laplacian condition, and I'm calling another condition. So I create another condition that now you don't have, that is called SVM Laplacian condition, and is a condition I use to impose this strange boundary condition. Okay.
Can you explain how you modify the weak form for the SVM?
Yes, yes. So I go on my Kratos, not much infusion, but I put in the same way. So in IJ application, custom condition, and I have my SVM Laplacian condition. So I have some additional terms because I use the derivatives because to impose this modified initial boundary condition and keep the same order, I compute. This is basic of IGA. Okay, I'm imposing the boundary condition on this surrogate boundary, and I'm doing a Taylor expansion between one Gauss point here and the closest point on the two boundary. Okay.
And how is the expression you are adding in the weak form?
Yeah, good question. So it's still a Nietzsche approach, but instead of this U, here I have U plus the Taylor expansion. So the gradient of U scalar D plus the transpose the second derivative of U D.
Where D is the distance between the surrogate boundary and the true boundary.
Yeah, this is the projection. Yeah, it's the projection between one Gauss point on the surrogate boundary to the closest point to the true boundary. Okay, so instead of this U and this U, in my weak formulation, I put this. Okay, but good question. Okay, so here, if you want to, we can do a meeting and I will explain all the terms I add. But you can see here that I set shape function derivatives to 6. Remember, with Ricky today, we were putting 2 because we didn't need so many derivatives. But with the SVM condition, I need, if I want to use 5th order basis function, I need up to the 5th derivative.
It all depends on the Taylor
expansion. Because I increase the polynomial order of the basis function, more derivatives I have to compute at each Gaussian point, only on this Gaussian point, not on all of them, just on this Gaussian point that I use to impose this Dirichlet boundary condition. Okay. What else? Nothing more. I can show you some examples. So also here I have a similar file conv main Kratos. So also here I put 3, for example, 3 not insertion. Okay, terminal. For example, let's set. Okay, let's see. Okay, I launch my problem. Okay, it's a bit big. Okay, this is the result. This is my parameter space. The blue dots are the Gaussian point, the integration point of the area. You can see if I zoom in. All right, so this is low. Okay, but you see the not span? No, you cannot see. Wait a second. Let's do a more coarse read. Let's do 11. Okay. Okay, now you can see all the north span. This shape is the embedded shape I chose. The green boundary is the solid boundary, so I implemented a way to compute that actually together with Andrea the solid boundary, and you can see each Gauss point that is connected to its projection for this distance d.
And what are the green lines?
The projection, just to connect, just to check visually if each Gaussian point is going to the actual projector or not. So just to verify. Okay.
Excuse me, just one thing. This is a simpler operation than the subdivision that Manuel was describing. Okay, so because this is just finding the closest point, and actually don't really need it to be the closest. Okay,
No,
it needs to be an approximation.
yeah, and
But you have to use as well a kind of search algorithm for
Yes.
finding the boundary.
yes, yes, of course, yes. For example, for the search to check if where is my solid boundary, we have developed like I can explain to you if you're interested. We have computed all the cut north span, and then we create like a snake that goes all around this the cut element. Okay, so for example, okay, this is cut, this is cut, this is cut. So if you identify these cut elements, you can go and start to construct your solid boundary. Okay.
Okay. So the point is identifying
The cut one, yes.
So for example, in your case, you have the real boundary which is in green, no?
Yes,
Like
the two boundaries, yeah.
And then we basically construct these projections on all the cut sets. I mean, then there is the hole inside, which is not cut, but this is also counted as, no?
Yeah.
As like, I mean, not as a cut cell, but okay,
Yes.
And then you do the projections and
Yeah, and
you have the boundary.
I cannot zoom in. I don't know why it's too heavy. Let's see. Yeah, and second. Okay. Is cursor, but I cannot zoom in. Okay, don't know why. But I was saying that you can clearly see the integration point on the boundary. The green line are connected to the integration point on the boundary. Okay, so we are cutting, but we are not integrating along the cut elements. This is the key feature. Okay, we are integrating a boundary term, that boundary term, with the niche approach on the surrogate boundary.
So you have no boundary. You can just eyes from that. Of course, it will be a bit less precise, but there are other advantages.
Yeah, let's see post process.
and what you have to do to recover the P+1 conversions rate?
Just considering the Taylor expansion up to the order you need. So if you're using quadratic basis function, you need to consider the gradient term and also the second order derivatives. If you consider all up to that order and you implement it well, you can. So you can see this is the absolute error, okay, with respect to the exact solution, and we see that there are error that comes from the Taylor expansion. Okay, the bigger errors comes from there. Okay.
Just to say, if it was not clear, it's like a fluid problem. So like a fluid domain with an optical inside, so you don't have to create the Gauss point inside the object. Just to say.
Yeah, a future application
inside of the object.
Yeah, a future application is like a fluid problem with a fluid flow that is coming from the left, and here there is an immersed immersed body where we want to import that the velocity is 0, for example. Okay. And let's see cost process of this. I took a more refined view. You see that the L2 norm of the error is very small, and yeah, now these peaks are at 10 to the minus 5. So we are.
And why in some ratios you have more error than in others?
Depends on the solution there, because maybe here the exact solution is very high with respect to here. So
Yeah, the gradient of the solution.
yeah, for example, yes. But let's see a convergence study of this case. Okay, also here I'm doing 3 steps. So we are launching Kratos 3 times, every time doing not insertion. Here we're using third order basis function. You see 2 and 2, and so we expect a fourth order velocity, and we are getting closer to this. Okay, so also with the internal boundary, we are still obtaining the optimal convergence. Okay, and I can of course change the shape, for example, using a circle. So I'm going to change this here. I can use a circle. Yeah, you see, it's the same problem with with an embedded circle, and you see you have the surrogate boundary that is made like this, and I can still have the same model of convergence.
And you have 9 quadrature points per element.
Yes, because it's p equal to 2, so
p plus 1.
p plus 1 in each direction, so 9 per, yeah, to decrease that, yeah. And another thing that we have done is to, instead of taking the external boundary as surrogate boundary, we can take the
inner one.
Also the inner, but also the one that's in the middle. So the best boundary where we can provide. So you can see here now that it's not the external, it's not the internal, but it's very close to the other one, because sometimes I go external, sometimes I go internal when I need it. So this is much better, and the error lower. Okay.
Sorry,
Yeah.
I got a bit lost. Now what did you change?
Now instead of taking the external boundary like I was doing here, now I'm taking. Maybe I can.
first example.
With a course. Yeah. Refinement. 11. Okay. Yeah. Here is the best example is the best boundary is exactly inside. Okay. But if I use a refine one,
Or you can use the pyramid.
and another embedded shape,
The one with four.
let's see. Hope that there are no problem, because sometimes I still have some bugs. This is another shape. Maybe you can explain better. Okay, this is clear. Okay, you see, it's not the external boundary. The external boundary would be like very far from the two boundaries. So we have to do a bigger Taylor expansion. So D would be a bigger, and so we would commit a bigger error. Instead, with the optimal boundary, you see, I'm always very close, at least, at most, 8h divided by 2, maybe, the distance. Okay.
And why do you change that in the code with this snake?
Yeah, it's still in the algorithm we have done, and it's a bit complicated maybe, but yes, actually the idea is that we check if the cut element is more inside or more outside. We have it's simple. The algorithm we we compute at 25 points.
So within the element.
Yeah, within the
The
knot
cut
span,
element.
exactly the cut knot span. Okay, and we check if the majority of this is inside or outside the two boundary. And so if it is outside, we consider it we let the boundary, the Soviet boundary, be outside or inside. Okay, we do it for each of the cut element, cut knot span.
And you said 25?
Yeah, but we could take a 16, or we could take more. I don't know.
But the less you take, the worse. off
Yeah, if you
are.
take only 9, maybe it might be that the position are not.
Clear.
We saw it with 25. It's pretty good. Yeah. Pretty good.
There's also a paper saying this.
There is also a paper of a professor that say that 25 is good. So good.
Okay.
Yeah, I think that's it. If you have a question about the implementation about yeah, this is actually a B red trimming. Okay, I'm not trimming inside the knot span, but I'm still using the same technology as they use, but I trim exactly along the knot values. Okay, so in this case, so that I don't have to integrate cut elements. That's it. Okay, if there are no questions, Ricardo, you wanna?
I mean, it's 4:44. Now, seriously. I think that definitely Nicolau, but many of you also, and Ricky, Andrea, Politini, you all listen to what to my lectures, right? So my proposal would be, for the ones, if you're interested, I'm willing to make an online. We meet online one day that we arrange. Just, right, you tell me when it would be good or less.
What would be the topic?
I mean, I have a presentation that is a bit about HPC, but it is about, let's say, optimization. So code optimization at first. So mostly it is the thing that we think that you should know about how a computer works. Right? So there's nothing difficult, but it is just a bit to understand how a CPU works, how the instruction workflow works, and this sort of things. Nothing at very high level, but I think it's important to make your code faster. Okay? And then there is a small presentation and a few small exercises done in Python for MPI and for and we speak a bit also of OpenMP. Right? OpenMP is for serial
Parallelization.
yeah, for parallelization, but on a shared memory machine. So right, to use the multi-cores that you have
I have already some with the so it works.
yes, no, yeah, but it is just to
I don't know
understand.
how it works.
I mean, to understand how it works. I have my own code there, now I want to make it run a bit faster. Okay? And it is a bit important to understand also, for example, what is the limitation or what are the sort of things you can expect. So we can do two things if you like. One thing is if you guys, but I could share, let's say, the material with you. And it's just a presentation that you can go through, okay? But then we can arrange a meeting. If not next week, I have a pretty busy week, but I mean, we can find and I will just do it online. Okay. Otherwise, I can do it in half an hour, but I think it is not. I mean, it's better that only who is interested, and only if you are interested, actually. Okay? And about the MPI, it is to understand how it works, right? So at least to know how you would address programming using a cluster, right? Which maybe is not the objective of your PhD, but I think is something it is important to be acquainted of. Okay. So I'm going to share with you the presentations. I would ask you guys, if you can write me, I will know to whom I should share this. Like, even if you guys already have, so
Yeah, yeah.
spam everyone, or I can just pass it to the notebook as you wish.
But you can upload it to the drive.
I can upload it to. And then we arrange privately, let's say, just one thing, this yes, just for me to repeat it once, to prove once, okay? And I will just do an online game, okay? So I will stop here. So honestly, it has been a pleasure, but I will not make any speeches. Okay, so I'm not into speeches, but Roland said it right. If you collaborate, you will look after all of it. So this is a big message. So.
It looks fine.
By the way, you should all have my phone number. If you need, you can always send me a WhatsApp, okay? Yes.
Yeah, right. Yes, actually, these are,
Enjoy Barcelona for the weekend. Stay tuned.
Thank you.
Thank you very much.
Oh, yeah, the computer, you need to give it back.
You
I always forget.
Of course, I will.
So we use the function
Yes, so Nicola, he gives the computer to you and you give it to me on Monday, right?
Yeah, I will, yeah, I'll leave it in my office.
That's fine. No?
So,
I will.
stops the.
So we expect you as in terms of like a polynomial of the two of the three. So then the gradient is the derivative of L. We cannot go into it. If you go a bit, it's 0, 0, 0. So